We call light the universe's ultimate constant, the one speed nothing can outrun. Yet, in a blunt and literal sense, no one has ever measured its speed in just one direction. Every measurement hides a quiet trick, a loophole baked into how we synchronize time itself. So if we can't clock light on a one-way trip, what exactly are we measuring when we map the cosmos in light years instead of miles? On a clear night, the sky is not scenery. It is a time machine, and every point of light is dated. We navigate by photons that refuse to carry a universal now, and that refusal changes everything we call distance. For centuries, a single number has been treated like bedrock, etched into textbooks, carved into instruments, and trusted without hesitation. Yet the deeper you look, the more that certainty depends on how we agree to keep time across emptiness. In the laboratory, light behaves with a discipline that borders on the absolute, returning the same result no matter how clever the apparatus becomes. Mirrors, resonant cavities, interferometers, each design tightens the grip on precision while quietly keeping the timing local. The moment we try to stretch a stopwatch across space, the problem stops being about hardware and becomes a question of meaning. Because simultaneous is not a simple word once distance enters the sentence, two perfect clocks can still disagree about what counts as together. You can build them identical, you can separate them gently, you can shield them from every obvious disturbance, yet their comparison still asks for a rule. And in physics, a rule is never merely a convenience. It is a commitment about how the world is sliced into moments. This is where the familiar comfort of miles begins to fail. A mile assumes a ruler that can be laid down all at once as if space were a passive stage. But the universe does not hand us a stage, it hands us signals, arrivals, delays, frequencies, and faint patterns that reach us only after long one-way journeys. Distance out there is not something we touch, it is something we infer from what light brings. So the light year is not a poetic indulgence, and it is not a surrender to scale. It is the unit that admits what observation really is, a record of travel time written into the sky, layered by causality. When we say an object is so many light years away, we're not switching from miles to metaphor. We're admitting that the cosmos is measured by messages. That admission has consequences. It means that the maps we draw are also histories, and the horizons we speak about are not just edges of sight, but boundaries of influence. It means the same constant that anchors modern metrology can also unsettle our intuition about here, there, and the thin line between them. And it means that the question we started with is not a technicality to be patched. It is a doorway into what space and time actually mean. Across this journey, we will follow the pursuit of light speed from early gambles and ingenious machinery to modern lasers and atomic time. We will step carefully through the puzzle of separated clocks, then into the bargain at the heart of relativity, where invariance is preserved and simultaneity is spent. From there, we will widen the view until space-time itself is no longer fixed, and the universe becomes the ruler we must learn to read. And when we return to the everyday world, navigation, satellites, and the quiet choreography that keeps your position from drifting, we will see how a chosen definition can be as real as any measurement. Not because physics is arbitrary, but because its most reliable facts are the ones that survive every coordinate system we can invent. By the end, the speed of light will look less like a mere number, and more like a boundary line between what we can observe and what we must define. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from the lab's closed loops to the sky's open paths, then out to expanding space where distance becomes time. Along the way, you will see why the light year is not a compromise, but the most honest ruler we have. We begin with a number that feels like bedrock, the kind you could carve into stone and trust. 297,792,458 meters per second. We call it C. On screen it looks clean, digits marching in a straight line, yet behind it sits a century of argument, experiment and careful definition. It is printed in textbooks, programmed into instruments, and quietly embedded in the way we teach space and time. In modern physics, C is the speed of light in vacuum, meaning light travelling through empty space with no glass, air or plasma to slow it. It also applies to any massless signal in relativity, including idealized electromagnetic waves in the absence of matter. In special relativity, c is not just very fast, and it is not merely a property of light bulbs. It is invariant for inertial observers, no matter how they move, and that invariance reshapes the meaning of time itself. That claim sounds like a clean experimental fact, the kind you could verify with a clever apparatus and a stopwatch. Measure light, get the number, and the universe agrees. Every lab, every decade, every continent. But the comfort of C hides a subtle gap between what we can measure directly and what we assume to interpret that measurement. The constant feels like a discovery, yet part of its power comes from how we choose to define our units. When laboratories measure the speed of light, they almost always measure a round trip because round trips are what clocks naturally like. Light goes out, reflects, and returns, tracing a closed path that begins and ends at the same instrument. You start one clock, you stop the same clock, and you divide distance by elapsed time, which sounds almost too simple. In practice, the setup can be a mirror down a long corridor, a retroreflector on a mountaintop, or a cavity where light bounces thousands of times. That method is powerful because it avoids a deeper problem that hides in plain sight. It needs only one clock sitting in one place, so there is no need to compare now here with now over there. With enough care, the round-trip value can be pinned down with astonishing precision, because errors can be averaged and systematic delays can be modelled. Interferometry turns tiny phase shifts into distances, and atomic clocks turn oscillations into time with remarkable stability. By the late 20th century, the number became stable enough that metrologists reversed the logic. Rather than measuring C with a meter stick, they used C to define the meter. The constant stopped being merely measured and started being used as a foundation. Today, the meter is defined so that C is exact by convention, which is a subtle but important change in the story. 1 meter is the distance light travels in 1 divided by 299,392,458 of a second. That second is itself tied to atomic physics, to a specific transition in cesium, counted again and again with microwave precision. So our rulers and our clocks are welded together through a chain of definitions that runs from atoms to light. So the constant everyone knows is also a constant we have chosen to bake into our rulers, making it feel immovable. That is not a weakness. Definitions are tools, but it means the number's certainty comes from a decision as well as an experiment. Because the documentary's mystery is not about the round trip, it is about the one-way trip. Imagine light leaving point A and arriving at point B, a straight shot across a room, a valley, or the gap between satellites. How long did that one-way journey take, measured as a departure time at A and an arrival time at B? To answer, you need a clock at A and a clock at B, separated in space but expected to agree about time. You must know what time it was when light left, and what time it was when it arrived, without ambiguity. Now the hidden ingredient appears, and it is more slippery than it sounds. Those two separated clocks must be synchronized, meaning they share a definition of simultaneity across distance. Synchronization sounds like a technical detail, like tightening a screw on an instrument, yet it is the hinge of the whole question. To sync distant clocks, you must send signals between them, and signals take time to travel. If you use light signals to synchronize, you're already assuming something about light's travel time, even if you do not say it out loud. You're smuggling in the answer you want to measure, because the procedure needs a rule for how long the signal took. This is the circularity that makes the one-way speed slippery, and it is not just a philosophical trick. Measuring it requires synchronized clocks, and synchronizing clocks requires a rule about speed, so the measurement and the convention intertwine. Visually, it is almost comical. Two clocks on opposite ends of a line, a flash in the middle, and a question mark hovering over the word simultaneous. The entire drama hangs on what we mean when we say two distant events happen at the same time. There are workarounds that look clever at first, and they often appear in popular explanations as if they solve the problem. You can carry a clock from A to B, or use cables, or use atomic standards, and each method feels like a practical escape. But each method hides assumptions about time and motion, and relativity is unforgiving about hidden assumptions. Moving clocks tick differently, even at ordinary speeds, and the difference is small but conceptually decisive. If you carry a clock slowly from A to B, you might hope it stays synchronized, yet slowly is not moving. The clock's path through space-time matters. its proper time depends on its motion, so transport becomes its own kind of convention. If you use a cable, you must know the signal's delay inside the material, and that delay depends on electromagnetic properties and temperature. Even the geometry matters, because bends and connectors introduce tiny lags that must be accounted for. If you use atomic standards, you still face the same comparison problem because standards tell you how a clock ticks locally. They do not, by themselves, tell you how to declare two distant ticks as belonging to the same moment. Even GPS, our most practical timing network, depends on relativistic corrections and a chosen synchronization convention that is applied consistently. Satellites carry atomic clocks, receivers solve for position and time, and the entire system works because the coordinate time is defined and maintained. GPS engineers do not debate simultaneity in the field, yet the system quietly assumes a global time coordinate in an Earth-centered frame. It is a triumph of applied relativity, proof that conventions can be operationally powerful when they are coherent. So the claim is not that light's one-way speed is unknowable in practice, or that we cannot build useful systems. The claim is that its value cannot be extracted without a convention, because the act of comparing distant times already chooses a rule. The round-trip speed is directly observable, because it uses one clock and a closed path that returns to the same place. The one-way speed is entangled with how we define simultaneity at a distance, which is a deeper kind of choice. This is where Einstein enters the story as more than a name attached to equations, and more than a face on a poster. Special relativity begins by defining how to synchronize clocks, because without that step the coordinates remain ambiguous. Historically, this was not a casual move, because 19th century physics was haunted by the idea of an ether, a preferred medium for light. Experiments like Michelson and Morley tried to detect Earth's motion through that medium, and they found no such drift in the round-trip speed. Einstein's standard choice is simple and symmetrical, and it fits the stubborn experimental pattern. Assume light takes the same time going from A to B as from B to A, so the forward and backward legs share the total equally. With that assumption, the one-way speed equals the measured two-way speed, and c becomes the speed in every direction for inertial observers. The geometry of spacetime becomes clean, and the equations take on a striking elegance. That choice is called the Einstein synchronization convention, and it is often taught as if it were forced by nature. It makes the laws of physics look simple, and it matches every experiment that tests round trips, from laboratory optics to particle accelerators. But it's still a choice about distant simultaneity, and the word choice matters here. It is a way of stitching time together across space, like laying a grid over a landscape so that every point gets a coordinate. Other conventions are logically possible, and they can be written down without contradicting any two-way measurement. They can assign different one-way speeds in opposite directions while keeping the same round-trip average, so the loop still closes with the same total time. Those alternatives do not change what any single clock measures on a closed path, and they do not let you send signals faster than causality allows. They change how we label events with time coordinates, and that relabeling can shift which events are called simultaneous. Here the documentary's tone shifts from familiar to strange, because the constant we treat as a physical limit begins to look partly like bookkeeping. We teach c as a speed you could, in principle, measure from here to there, yet the one-way value may depend on the coordinate rules. That does not mean anything goes, and it does not mean physics becomes subjective. The two-way speed remains fixed, and causal structure still constrains what can influence what, because the light cone remains the boundary of possible cause and effect. In relativity, c marks the boundary between time-like and space-like separation, separating what can be reached by slower-than-light motion from what cannot. It sets the shape of light cones, and those cones organize the possible ordering of causes. Visually, think of a cone of light expanding from an event, a luminous geometry drawn in the dark. Inside the cone, influences can travel. Outside it, events may be separated in a way that no signal can bridge without breaking the rules. So something deep is physical, even if one piece is conventional, and that is the tension worth holding. The question becomes which parts of C are nature, and which parts are our map, because maps can be chosen while landscapes resist. This matters because our map is how we measure the universe, and measurement is never just reading a dial. When we talk about distance in space, we quickly stop using miles, because the scales become too large for human intuition. We switch to a unit that sounds like time, and the shift is almost poetic. We say light year. A light year is not a year of waiting, and it is not a measure of duration. It is a distance, defined as how far light travels in vacuum in 1 year, using the same C that anchors our meter. That definition mixes timekeeping and distance on purpose, and it reveals how physics converts between them. It turns the speed of a light into a conversion factor between meters and seconds, letting time become a ruler when space is too vast for tape measures. In everyday life, we already do this quietly, and nobody finds it strange. We say a friend is 10 minutes away, and we mean a distance by a time because travel time is easier to feel than kilometers. Cosmology does the same thing at a grand scale, and it does so because light is what carries information to us. Telescopes do not touch galaxies. They collect photons, count them, and reconstruct histories from their arrival times and wavelengths. When we look at a galaxy, we see it as it was when the light left, and that is not metaphor. Distance and look-back time become inseparable, because every image is also a delayed message written in electromagnetic waves. A light year makes that connection explicit, and it gives the mind a handle on deep time. It tells you how long the information has been in transit, and it quietly reminds you that observation is always about the past. But the earlier puzzle returns, sharper now that the stakes are cosmic rather than laboratory-sized. If one-way light speed depends on synchronization, what exactly does light travels in a year mean when the journey's not a closed loop? The answer is that the light year relies on the same structure that makes C useful, and that structure includes conventions that are chosen for consistency. It relies on a coherent way to relate time and space, so that different observers and instruments can compare results. In practice, astronomers use models, standard candles, radar ranging, and parallax, and they cross-check methods because no single technique rules the sky. Many of those methods are ultimately round-trip or geometric, grounding distance in angles, periodicities, and echoes. Even when the language is light travel time, the operational core often comes from closed path measurements or from geometry that avoids distant clock comparisons. The sky becomes a triangulation problem, stitched together by repeated observations and consistent timing standards. Yet the language of light travel time remains central, because our observations are built from received signals and clock readings, and because the universe communicates through light. Every spectrum is a timestamp of physical processes, and every pulse is a marker in a vast timing network. The deeper point is not to undermine astronomy, and it is not to suggest that distances are arbitrary. It is to reveal the scaffolding that makes cosmic measurement possible, the hidden framework of definitions that keeps our inferences stable. We live inside a web of conventions that are chosen because they work, and because they make the laws simple enough to use. They are chosen because they make predictions accurate, and because they let different experiments speak the same mathematical language. But once you notice the web, you can ask sharper questions, and the questions feel less like wordplay and more like diagnostics. Is simultaneity a discovered fact, or a defined relationship that helps coordinate distant measurements? Is the one-way speed of light a measurable property, or a coordinate choice that leaves all measurable round trips unchanged? If two conventions predict the same closed-loop times, what does it mean to say one is truer than the other? If it is partly a choice, why does nature seem to prefer the Einstein choice, at least in how neatly it organizes the equations we use? Why do the laws look so symmetric when we adopt it, and why does that symmetry feel like a clue? And if we change the convention, what would change in our descriptions of motion, causality, and cosmic distance, even if the raw observations stayed the same? Would the story of the universe read differently, simply because we chose a different clock rule? These questions are not philosophical decoration, and they are not asked only in seminar rooms. They sit inside technologies that depend on timing, from navigation to communications, where nanoseconds can translate into meters of position error. They also sit inside cosmology, where the universe's expansion is inferred from light that has crossed billions of light years, and where timing and distance are braided together. When we say far, we often mean long ago, and that dual meaning is built into the measurements. So the opening claim becomes a challenge, and it is more unsettling the longer you sit with it. We know C with exquisite precision, and we use it to define our units, yet the simplest sounding measurement, the speed of light from here to there, is not something we can read off nature without first choosing a clock rule. That is the tension this documentary will follow, and it will not resolve by dismissing either side. A constant everyone knows, and a measurement nobody makes, at least not without quietly deciding what synchronized means. Next, We will build the problem carefully, starting with how clocks are synchronized and why simultaneity is not absolute. Then we will ask what experiments really test, what they leave open, and why the cosmos is measured in years instead of miles. We ended with a clean number and an unclean question, and that contrast is the engine of this chapter. We can measure the round-trip speed of light with one clock, because one device can mark both departure and return. We cannot measure the one-way speed without first choosing how distant clocks share now, a choice that sounds philosophical until it becomes experimental. Chapter 2 follows the chase from intuition to precision, and it does so with a recurring visual rhythm. Each era invents a smarter stopwatch, then discovers the same trap hiding in the design. The most reliable tests make light leave and return, because loops let one clock do all the accounting. The loop is not a gimmick, it is a way of keeping time local. The story begins before c was a constant, when fast still meant too fast to catch in any practical sense. In the early 17th century, Galileo tries to turn speed into a measurement, and he does it with the tools of his age: human senses, hand-timed actions, and a landscape used as laboratory. He imagines two observers on distant hills, each holding a shuttered lantern against the night. Picture the scene as the camera finds it: a dark ridge line, a cold wind, a small flame behind oiled glass. The two hills are separated by a few kilometers of air that looks empty, but is full of turbulence and haze. Galileo's plan is simple in principle and doomed in practice, which is often how measurement begins. Observer A opens his lantern, and Observer B watches for the flash, then opens his own lantern immediately. Observer A measures the delay between sending and receiving, then subtracts reaction time, hoping the remainder is light's travel time. The subtraction is the problem, because reaction time is not a small correction that can be treated as noise. Human perception and muscle movement take tenths of a second, even when trained and alert. Light crossing a few kilometers takes microseconds, so the signal is buried under the biology. Even the word microsecond exposes the mismatch, because it names a timescale Galileo cannot access. A microsecond is a millionth of a second, and the nervous system does not resolve that granularity. The lantern shutter adds its own delay, because it must move through a finite angle and overcome friction. The atmosphere adds uncertainty too. Scattering and dimming can blur the moment the flash becomes noticeable. Galileo learns something more important than a number, and the lesson is methodological rather than optical. He learns that very fast is not the same as measurable, because measurement is always a comparison against a standard. To measure speed, you need a clock that can resolve the travel time, or a method that stretches the effect into a larger, more legible difference. Without that stretch, the experiment reports the limitations of the observer, not the properties of light. That need drives the next conceptual leap, and it is a leap about scale. If you cannot slow light down, you can make the path longer, so the travel time grows into something your instruments can notice. If you cannot make the path long enough on Earth, you can let the sky provide the baseline. The heavens become a measuring tape, not because they are mystical, but because they are vast. Astronomy becomes the first workable laboratory, because the solar system supplies distance for free and repetition for free. In 1676, Ola Roma studies Jupiter's moon Io, a small world that slips into shadow with a regular rhythm. Io disappears into Jupiter's darkness like a cosmic metronome, and that regularity is the precious resource. A periodic event is a clock you can read from far away. The eclipses should repeat with a predictable period, because orbital motion is governed by stable geometry and gravity. Yet Roma sees the times drift across the year, and the drift is systematic rather than random. When Earth moves toward Jupiter, eclipses arrive earlier than expected, as if the signal has less distance to cross. When Earth moves away, eclipses arrive later, as if the signal is delayed by extra space. The visual here is subtle but powerful: Earth tracing its orbit, Jupiter farther out, and a line of sight that stretches and shrinks like a breathing cord. Roma interprets the drift as light travel time changing with distance, and the interpretation is daring because it treats light as finite. The clock is orbital mechanics, because the period of Io is stable enough to predict. The ruler is Earth's changing position in its orbit, because that changing position changes the distance to Jupiter. The measurement is not a direct stopwatch on a beam, but it is quantitative, and it is anchored in a repeated pattern. Römer estimates that light needs on the order of minutes to cross the diameter of Earth's orbit, which we now call the astronomical unit scale. The exact value is rough by modern standards, yet the logic is decisive and difficult to unsee. Light is not instantaneous, and its speed can be inferred from timing. Römer's method also hints at a theme we will keep returning to, because it solves a timing problem by refusing to create one. The key observable is a difference in arrival times at one location, recorded by one observer with one local clock. The inference uses geometry and periodicity, turning a drifting schedule into a speed. The measurement avoids synchronizing two distant clocks, and that avoidance is not an accident. It is the reason the method works, and it is the reason it survives criticism. You can argue about ephemerides, telescope timing, and the exact moment an eclipse begins or ends. You can question the sharpness of the shadow boundary, or the observer's ability to mark a transition. But you do not need to define simultaneity between Earth and Jupiter, because you are not comparing two separated clocks, only a pattern against itself. As the centuries turn, the chase comes back to Earth, and the ambition becomes more direct. The goal becomes a terrestrial time-of-flight experiment, where a beam's travel time is measured in the laboratory. The challenge is to build an apparatus that turns microseconds into something a human-scale instrument can register. The camera can linger on brass, gears, and polished glass, because the story becomes mechanical. By the 19th century, physics is learning to trust instruments that amplify tiny effects. Experimenters build devices that convert time into motion and motion into a visible mark. They also learn to isolate variables, because the smallest delays matter. Temperature, vibration, and alignment become characters in the plot, silent, stubborn, and always present. In 1849, Hippolyte Fizeau designs a machine that forces light to announce its travel time mechanically. A beam passes through a gap in a rapidly spinning toothed wheel, and the wheel becomes a chopper that slices time into windows. The light travels to a distant mirror and returns along the same line, retracing its path through the air. The distance is long enough to matter, yet short enough to control. At certain wheel speeds, the returning beam is blocked by the next tooth, and the bright point vanishes. At other speeds, it slips through the next gap and the light reappears, as if the apparatus is blinking. The wheel's rotation rate becomes the clock, because each tooth and gap defines a known fraction of a turn. The distance to the mirror becomes the baseline, because the beam's path length is twice that distance. Fizeau can compute the travel time from the wheel speed at extinction, because extinction marks a specific timing condition. The method is ingenious and still fundamentally a round trip, even though the language tempts us to call it one way. Light goes out and comes back to the same instrument, and one clock reads the whole journey. The wheel and the observer sit together, so the timing is local. That loop is not a convenience, and it is not merely tradition. It is the structural reason the result is clean, because it avoids the need to compare a start time there with a stop time here. The wheel does not care what time it is at the mirror. The mirror is passive, and the only active timing element is at the source. A few years later, Léon Foucault improves the approach by trading teeth for angles, and the improvement is as elegant as it is practical. In his rotating mirror experiment, a beam reflects off a spinning mirror, travels to a distant fixed mirror, then returns to the spinner. The apparatus looks almost like a magician's trick because a tiny twist becomes a visible shift. The key is that the mirror keeps turning while the light is away. During the light's flight, the rotating mirror turns slightly, and that slight turn changes the angle of the returning reflection. The returning beam reflects at a different angle, producing a measurable displacement on a screen or in an eyepiece. The rotation rate is the clock, because angular speed is known and controllable. The geometry converts tiny time into a larger spatial shift, which is easier to measure precisely. Foucault's setup can be compact and precise, and it is less dependent on long outdoor baselines. It also makes the round-trip nature even more obvious, because the same rotating mirror both launches and receives the beam. The time is encoded in a change that accumulates only because the light returns. Without the return, there is no second reflection to reveal the mirror's motion. Both Fizeau and Foucault are called time-of-flight measurements, and they are, but the phrase hides a crucial detail. They are time of flight on a closed path, where the measurement is a total travel time. The apparatus measures an interval, then divides by twice the distance, producing a speed. The division is mathematically simple, yet conceptually loaded. This is the recurring tension. and it becomes clearer with every improvement in technique. Every time we try to catch light in one direction, the experiment quietly adds a return leg, because the return leg is what makes the timing self-contained. The return leg is what lets a single clock define the interval without any synchronization argument. The loop is the experimental escape hatch. By the late 19th century, optics becomes a precision science, and the workshop becomes a temple of alignment. Michelson refines rotating mirror methods and pushes baselines longer, extracting cleaner numbers from cleaner geometry. The numbers converge and the uncertainty shrinks, because systematic errors are hunted down one by one. The measurement still comes back to the same operational call, out and back, counted by one local timing system. Then relativity arrives and changes what the number means, without changing the practical need for careful measurement. The speed of light stops being only a property of electromagnetic waves moving through space. It becomes a structural constant tying space and time together, and it becomes central to how clocks are compared. In that new framework, C is not just fast, it is foundational. That shift makes the measurement problem sharper, not softer, because it forces us to notice what we used to ignore. If simultaneity is not absolute, then synchronizing distant clocks is not a neutral step that can be taken for granted. It is a convention that must be stated, even when it is hidden inside procedures. The more carefully you define time, the more you must explain how time is shared. The 20th century brings new tools that seem, at first glance, like they should break the loop. Electronics can resolve nanoseconds, turning pulses into crisp edges on oscilloscopes and counters. Atomic transitions can define seconds, giving time a reproducible anchor that does not drift like a pendulum. Lasers can produce stable frequencies and coherent beams, making light itself a precision instrument. Modern metrology often measures C through frequency and wavelength, because those quantities can be compared with extraordinary resolution. Interferometers compare phases along different paths, and phase is a kind of clock hand that advances every cycle. A shift of fringes becomes a distance, because each fringe corresponds to a fraction of a wavelength. The clock is an oscillator, and the ruler is a wavelength tied to that oscillator. In interferometry, light often travels out and back in arms of a device, reflecting from mirrors that define the path. Even when paths differ, the observable is a phase difference measured at one detector, not a timestamp read at two locations. The measurement is local because the detector is where the comparison happens. The comparison is internal to the apparatus, because the paths are brought back together before anything is recorded. The visuals can be almost abstract. Two beams splitting, sliding along perpendicular corridors of vacuum, then recombining into bright and dark bands. Those bands are not decoration, because they encode path differences with sub-wavelength sensitivity. A tiny change in length produces a measurable shift in intensity, and that shift can be counted. The experiment is, again, a loop, made of phase rather than gears. Microwave cavities push the same idea into resonant boxes, where waves bounce back and forth until only certain patterns survive. A cavity supports standing waves only at specific frequencies, and those frequencies are sharply defined by boundary conditions. The allowed modes depend on the cavity's size and the wave speed, because the wave must fit an integer number of half wavelengths. Measuring resonance ties length to time standards, because frequency is counted in cycles per second. The core trick is always to replace a stopwatch with a frequency, because frequency is countable with extreme precision. Atomic clocks turn time into a stable count of cycles, based on quantum transitions that are the same in every identical atom. Once you can count cycles, you can compare signals with extraordinary sensitivity, and you can average away noise. The experiment becomes less about reflexes and more about statistics. As clocks improve, the direction of definition reverses, and that reversal is one of the quiet revolutions of modern science. Instead of using a meter stick to measure C, metrologists use C to define the meter, because time is the more stable reference. In 1983, the meter is defined as the distance light travels in 1,299,792,458 of a second. The number becomes exact, not because nature is forced, but because units are chosen. That definition makes C exact by convention, and it moves uncertainty into the realization of the second and the practical realization of length. The constant becomes part of the unit system, welded to timekeeping and reproducibility. Laboratories do not discover C anew each day because the unit system bakes it in. What they test instead is whether their clocks and lengths realise the definition correctly. This is not a retreat from measurement, and it is not a surrender to abstraction. It is a recognition of what we can measure best, and what we can reproduce most reliably across continents and decades. We can measure time and frequency more precisely than any physical rod, because rods expand, bend, and age. We can reproduce atomic transitions anywhere on Earth, because atoms do not remember where they were made. So the modern story sounds like total victory, and in many ways it is. We have lasers locked to atomic references, and their frequencies can be counted like the ticks of an impossibly fast clock. We have interferometers that resolve fractions of a wavelength, turning nanometers into readable signals. We have cavities that turn geometry into frequency with breathtaking stability, so that length becomes a spectral line. Yet the documentary's central question survives all of it, because it is not defeated by better hardware. These methods measure the two-way speed, or they measure quantities that assume a consistent synchronization inside a single frame. They do not extract a one-way speed without a convention, even when the apparatus looks one-directional. The loop remains either in the optics or in the mathematics. The reason is structural, not merely technical, and it can be stated plainly even as the implications deepen. A one-way measurement needs a departure time at A and an arrival time at B, separated in space. That requires two clocks at different places, and those clocks must already agree on what counts as simultaneous. Without that agreement, travel time is not a single number. If you try to synchronize them by sending a light signal, you must assume something about the signal's travel time, which is the very quantity you hope to measure. If you try to synchronize them by transporting a clock, you must account for motion and relativity, because moving clocks do not keep time identically in all frames. If you use cables, you must model delays, dispersion, and electronics, and those models become part of the definition. Every workaround either becomes a round trip, or it smuggles in a rule that plays the role of Einstein synchronization, even if it is disguised as engineering detail. The better your instruments get, the more visible the rule becomes, because the remaining uncertainty is no longer mechanical. Precision turns hidden assumptions into dominant terms, and the experiment starts to measure its own definitions. This is why the historical chase matters, and why it belongs in a documentary about a modern constant. Galileo fails because the clock is too slow, and because the human body is the limiting instrument. Roma succeeds because orbital timing stretches the effect and keeps the timing local, turning distance into delay without distant synchronization. Fizeau and Foucault succeed because they build loops that let one clock speak, while the far mirror stays silent. Modern laboratories succeed because they turn light into a frequency problem, and frequency is the most measurable thing we have. They still close the loop, either physically with reflections or mathematically with phase comparisons at one location. The photon is chased into cavities, fibers, and interferometers, but it is still asked to return. The return is what makes the accounting unambiguous. So the tension builds toward a paradox that is not about engineering, and not about the cleverness of the apparatus. We can define and measure C with extreme confidence in round trips, and we can verify that confidence across technologies and centuries. We can build systems that depend on that confidence every second, from ranging to timing to navigation. Yet the one-way value remains tied to how we define distant now, which is a different kind of constraint. This is the pivot point for the rest of the documentary, and it is where mystery replaces triumph. The more we chase light with better clocks, the more we discover that the missing piece is not speed. The missing piece is simultaneity, and simultaneity is partly a choice. The choice can be reasonable, consistent, and useful, but it is still a choice. Because the documentary's mystery is not about the round trip, it is about the one-way trip. Next, we move from apparatus to assumptions. We will build synchronization carefully and show why different conventions can preserve every loop measurement while changing the one-way story. That is where the light year returns with new weight, because it is both a distance and a time story told in the language of C. If distance is defined through light travel time, then our cosmic ruler depends on the same conventions that make one-way speed slippery. The universe is still measurable, and the measurements still work, but the language of measurement matters. What exactly are we assuming when we say two distant events happen at the same time? We chased a photon from lanterns to laser cavities, and the chase delivered precision with every generation of tools. It also delivered a boundary, and boundaries are where the deepest definitions live. Light speed is a measured fact in loops, confirmed by every method that brings signals back home. The one-way narrative depends on how we stitch time across space, and that stitching is the next thread we will pull. Because the documentary's mystery is not about the round trip, it is about the one-way trip. Speed sounds like the simplest ratio in science, almost too clean to be controversial, because it is just distance divided by time. Yet the simplicity hides an operational trap, one that only appears when time must be read in two places. In a lab, distance can be laid out with rulers, lasers, and calibrated baselines, and the camera can linger on the quiet certainty of a marked meter bar. Metrology turns length into procedure, with interferometers counting fringes and surveyors chasing alignment until the geometry stops drifting. Time can be counted with one clock if the signal returns, and that single dial is the key. When the start and finish happen at the same instrument, you never ask what now means somewhere else. That if matters, because a return collapses the problem back onto one place, one device, one dial, one local comparison. The measurement becomes a closed loop, and closed loops are where experimental physics feels safest. One-way speed demands something stricter, and it demands it every time you try to speak precisely. You need a departure time at A and an arrival time at B, and those two readings must be commensurable. That requirement hides inside the word time, which suddenly stops being a single number on a single instrument. It is two local readings that must share a standard, even when they are separated by kilometers of air, cable, or vacuum. A clock at A can tell you when the pulse left, down to nanoseconds if you pay for the right hardware. A clock at B can tell you when the pulse arrived, with the same crisp digits glowing on its face. But those readings only become a travel time if the clocks are synchronized, and synchronization is not just set them equal. Synchronization means they agree on what counts as the same moment, not merely the same label. This is where the circularity begins, and it begins so quietly that it can sound like philosophy. To synchronize distant clocks, you must exchange signals, and those signals take time to travel. If you already knew the one-way travel time, synchronization would be easy, almost trivial, because you would just subtract it out. But synchronization is exactly what you need to define that travel time, so the procedure folds back on itself. Make it tangible with a simple thought experiment, and let the visuals do some of the work. Two friends stand at opposite ends of a long tunnel, separated enough that shouting becomes useless, and hand signals dissolve into darkness. The tunnel is straight, dark, and lined with repeating concrete rings, so every meter looks like every other. At one end is point A, at the other is point B, each marked by a small tripod and a clean reference plaque. Each friend has an identical atomic clock and a button that emits a flash, and the flash is sharp enough to register as a clean electronic event. They want to measure the flash speed from A to B, as if it were a simple stopwatch problem. They agree on the tunnel length using a tape and careful surveying, and we can show the slow, methodical work of marking reference points. They also agree their clocks tick at the same rate, because identical frequency standards can be tested side by side. The missing step is not ticking, and it is not craftsmanship with the tape. The missing step is aligning the 0 point across distance so that 12 o'clock means the same slice of reality at both ends. If A says the flash left at 12,000 dirhams, B must know what 12,000 means at B, not just at A. That's a statement about simultaneity, even if it arrives disguised as bookkeeping. Simultaneity sounds like ordinary language, but in physics it is a rule for labeling events. It answers the question, which distant events share the same time coordinate, and therefore can be compared as if they were at once. You can try a naive method because it feels like common sense. Set both clocks to noon, then separate them, and trust that identical machines will remain in step. But the act of separating them is a motion through space-time, and the camera can follow the clock being carried away like a fragile artifact. Relativity says moving clocks accumulate different proper time than stationary ones, even when the motion looks gentle. Proper time is the time a clock measures along its own path, and it is the quantity that remains physically attached to the device. It is what the clock feels, because it depends only on the clock's world line, not on anyone's coordinate grid. Even if you move slowly, slow is not zero, and the difference is not a mere technicality. The transported clock's reading depends on its path and the frame used to describe it, which means the transport is already a choice. So the naive method becomes slow clock transport, a phrase that sounds like a workaround but behaves like an assumption. It quietly imports expectations about isotropy and inertial motion, and it treats those expectations as if they were measurements. If the world is perfectly isotropic in your chosen inertial frame, slow transport approximates Einstein synchronization, and the approximation can be extraordinarily good. If not, the method cannot certify one-way speed, because the very act of carrying smuggles in direction-dependent effects. The deeper point is operational, and it is the kind of point experimentalists learn the hard way. Any procedure that claims to compare distant times must specify how distant simultaneity is defined, because the definition is the bridge between two clocks. Historically, this problem did not arrive with Einstein as a novelty, because it was already hiding in telegraphy and longitude. To coordinate railways and maps, you needed a way to say now in two cities, and to make that claim actionable. Before atomic clocks, people used astronomical observations, pendulums, and time signals, and they learned that same time is a constructed agreement. The modern version simply makes the construction explicit, replacing church bells and star transits with cesium transitions and fiber links. Einstein's move was to make that definition explicit and to make it simple enough to use. He did not start with a one-way measurement, because the measurement needs the definition in advance. He started with a synchronization rule, and the rule is framed in the language of what you can actually record. Place clocks at A and B, and imagine them mounted on stable platforms, shielded from vibration and temperature drift. Send a light signal from A to B, then reflect it back from B to A, like a ping on an empty line. A records the departure time T1 and the return time T3 on its own clock, and those two marks are local and unambiguous. B records the reflection event on its own clock at time T2, which is also local at B. Now comes the convention that feels like physics, because it fits our intuition about symmetry. Assume the travel time A to B equals the travel time B to A, at least in an inertial frame with no preferred direction. Under that symmetry, the reflection at B is defined to occur halfway between T1 and T3, as read on A's clock. B sets its clock so that T2 equals T1 plus T3 divided by 2, and the rule becomes a recipe. This is Einstein synchronization, and it is elegant because it uses what you can actually observe: round trips and local stamps. It uses a round trip, one local clock at A, and a rule that splits the total time evenly. Once you adopt it, the one-way speed from A to B becomes C by definition, and the definition is baked into the clock setting. The equality of one-way speeds in opposite directions is built into the coordinate system, and that is the reveal. It is not a trick, and it is not a hidden manipulation of data, because it is openly a choice of coordinates. It is a coherent coordinate choice that makes the laws of physics simple in inertial frames, which is why it became standard. The equations of electromagnetism written in that language look the same in every direction, and that directional sameness is part of the appeal. The coordinate grid becomes clean, and the camera can show it as a neat lattice laid over the tunnel. It also matches every experiment that measures the round-trip speed, from early optical setups to modern resonant cavities, because those experiments constrain the total out and back time. So the one-way value is not extracted from nature in the same way, like a mass on a scale. It is inferred after choosing how to assign times at separated places, and the inference is only as unique as the convention. The mystery sharpens here, because the choice looks optional, but the consequences look physical. If Einstein's split is a convention, could we choose a different split and still match all round-trip data without breaking anything we can test? This question has a history, and it has been argued in papers and classrooms for decades. Hans Reichenbach formalized that freedom with a parameter called epsilon, which packages the ambiguity into a single dial. Epsilon labels a family of synchronizations consistent with the same two-way speed, and it does so with a simple bookkeeping rule. It keeps the measured round-trip time between A and B fixed, while allowing the forward and backward assignments to slide. Let the forward leg take an epsilon fraction of the total, and the return leg take 1 minus epsilon. If epsilon equals 1/2, you recover Einstein's symmetry, and the tunnel looks time-symmetric in both directions. If epsilon differs, the one-way speeds differ in opposite directions, and the difference can be made as dramatic as you like in coordinates. One direction can be assigned faster travel, the other slower, while the round-trip average remains locked. In that scheme, light could be assigned a faster speed one way and a slower speed the other way, without contradicting the round-trip measurement. The average over the closed loop stays fixed, and the instruments that only see loops cannot tell the difference. The key is what remains invariant, and the narrator can slow down here because it is the anchor. Any closed path measurement that starts and ends at the same clock gives the same result, because it never asks for distance simultaneity. Interferometers, cavities, radar echoes, and timing loops still agree on the same constant, because they are built from returns. The two-way speed remains c, and that constancy is what experiments have hammered into place with extraordinary precision. In flat space-time, with standard assumptions about local physics, changing epsilon does not change empirical predictions for experiments that depend only on round trips. It changes the coordinate description, which means it changes the story you tell about when distant events occurred. It changes what you call simultaneous at a distance, which is a deep change in language but not in local outcomes. It changes how you assign times to events at B, and therefore how you narrate the same sequence. This is where people worry about what is at stake, because the phrase speed of light carries cultural weight. It can sound like the speed of light becomes a matter of opinion, as if physics were negotiable. But the measurable content is not up for grabs, and the world does not become arbitrary. Causal structure remains, and light cones remain, because they are determined by the invariant interval structure that round-trip measurements constrain. The boundary between possible influence and impossible influence remains, and it remains as a geometric fact about space-time intervals. Events outside the light cone cannot be connected by signals, regardless of how you label distant clocks. Even under different synchronizations, you cannot build a device that sends a controllable signal outside the causal order defined by the two-way constant. You cannot engineer a violation by renaming times, because the constraints appear in what can actually coincide and interact. The convention reshuffles labels, not outcomes, and that distinction is the quiet heart of the chapter. It changes the bookkeeping of time coordinates, not the observed coincidence patterns in local measurements, which is what experiments ultimately register. Still, the one-way story feels physical because it sounds like a travel time, like a stopwatch reading. The problem is that travel time across space already assumes a shared now, and that shared now is exactly what is being defined. Bring it back to the tunnel and let the audience see the numbers on the displays. Suppose A sends a flash at its 12,000 astuilo, and the flash blooms briefly against the concrete rings before vanishing. B receives it and writes down 12,005 on its own clock, and the digits look authoritative on the screen. That number is meaningless until we know how B's clock was synchronized, because the offset could have been chosen differently. If B was set by Einstein's midpoint rule, the difference becomes a one-way travel time that matches C. If B was set by a different epsilon, the difference changes, and the same physical flash acquires a different duration in the coordinate story. Nothing about the flash changed, and nothing about the tunnel changed. Only the time coordinate assigned to the reception event changed, which is why the mystery feels like it lives in the definition of time itself. This is why one-way measurement cannot be purely mechanical, like weighing a rock or measuring a rod. Any method that claims to avoid synchronization must show where the shared time standard came from, and how it avoids smuggling in the same assumption. Consider the popular escape hatch of using a cable, because it sounds like a physical shortcut. Send an electrical pulse from A to B through a wire, then compare times, and pretend the wire is a transparent conveyor of now. But the cable has a propagation delay, and the delay is not a single magic number stamped on the insulation. It depends on material properties, temperature, dispersion, and impedance mismatches, and each of those variables can drift during the measurement. In real cables, the signal is not a perfect step, and different frequency components travel differently, especially over long distances. Reflections from imperfect terminations can shift the perceived arrival time, and the oscilloscope trace can show ringing that blurs the moment of arrival. To calibrate the delay, you typically send a signal down and back, or you compare against a known standard, and the calibration becomes a round-trip measurement. The loop closes again, and the one-way claim quietly returns to a two-way foundation. Even if you trust the cable model, you are still adopting an assumption about signal speed in the cable, and that assumption plays the same role as epsilon. It is a synchronization choice in disguise, because it tells you how to translate an event at A into a time at B. Consider a second escape hatch, the one that sounds most honest to intuition. Use two identical clocks, synchronize them side by side, then carry one to B and insist that the moved clock carries the same time with it. If you carry it very slowly, you hope it stays synchronized, and the scene can show careful hands moving a clock on a cart. But special relativity says moving clocks tick differently relative to the lab frame, and the difference accumulates continuously along the path. The transported clock measures its own proper time, which is real and local and indisputable. The comparison you want is coordinate time between A and B in a chosen inertial frame, and that is a different object than proper time. To convert proper time along a path into a coordinate synchronization, you must assume a frame and assume isotropy of space in that frame. Without those assumptions, the transport is not a neutral act, because direction and motion become part of the definition. In the limit of slow transport in an inertial frame, the transported clock approaches Einstein's synchronization, and the convergence can be calculated. That is not an independent measurement of one-way speed, because the endpoint agreement is achieved by leaning on the same symmetry. It is a different route to the same convention, justified by symmetry assumptions about the frame, and the symmetry is the quiet premise. The method works because you already decided what uniform means, and because you assumed no preferred direction in the underlying physics. Now connect this to the broader claim of relativity, because the chapter's puzzle lives inside that famous sentence. Special relativity says C is the same for all inertial observers, and that slogan is often heard as a direct statement about one-way motion. That statement is usually read as a one-way claim, like light always travels at C from here to there. But operationally it is grounded in round-trip invariance, and in the Einstein convention that defines simultaneity, which is why the theory needs both measurement and definition. The theory becomes predictive because the convention is applied consistently, and consistency is what turns definitions into usable tools. Coordinates become a shared language, and the laws take a symmetric form that makes conservation principles and field equations easier to state. Reichenbach's parameter shows that other languages are possible, and the camera can hint at alternate grids overlaying the same events. They are less convenient, often more awkward, but not ruled out by two-way tests alone, which is why the ambiguity persists. So why do physicists treat Einstein's synchronization as standard, almost without comment? Because it makes inertial frames look isotropic and keeps the equations simple, and because simplicity is not just aesthetic, it reduces the number of direction-dependent correction terms. It also aligns with how we build practical timing systems, where complexity has a cost in error budgets and maintenance. Engineering prefers conventions that minimize directional corrections and keep networks stable, especially when thousands of devices must agree. GPS is a useful analogy here because it turns synchronization into infrastructure rather than debate. Receivers solve for position by comparing signal arrival times from satellites, and those comparisons only make sense inside a defined coordinate time. Those comparisons rely on a defined coordinate time in an Earth-centered frame, and that frame is maintained by a network of ground stations and atomic standards. The system works because the convention is maintained consistently, and because every correction is computed within the same chosen language. GPS also reminds us that clocks do not float outside physics, as if time were a pure abstraction. They're corrected for gravitational and kinematic time dilation, and those corrections are not optional if you want meter-level accuracy. Those corrections are computed within a chosen coordinate system, and the corrections must be applied in a disciplined way. The system's success shows that conventions can be operationally powerful, not merely philosophical, because they let hardware agree on what simultaneous means. At this point, we can state the boundary clearly, and it is a boundary that clarifies the mystery rather than dissolving it. The invariant, directly measurable quantity is the round-trip speed of light, because it can be tied to one clock and one location. The one-way speed is coordinate-dependent under standard assumptions, and that dependence is not a defect in the theory. It depends on how you define distant simultaneity, which is a convention, and conventions are part of how physics becomes computable. That does not mean nature is silent, and it does not mean anything goes. Nature fixes the causal structure and the two-way constant with extraordinary rigidity, and it punishes any attempt to violate that structure with failed devices and inconsistent observations. What nature does not fix uniquely is the split of a round-trip time into two one-way times, absent an additional convention. The split is underdetermined by the closed-loop evidence, and that underdetermination is the hidden hinge. This is the hidden convention inside the phrase one way, and it hides because language makes it sound automatic. The phrase sounds like a simple measurement, but it is partly a definition, and the definition is what makes the measurement interpretable. And that raises a thought that is easy to miss in everyday science communication. When we say, it took 5 nanoseconds to get there, we're also saying what we mean by there at the same time, and we rarely announce that second claim out loud. Now the chapter turns toward the cosmic scale, where the same issue becomes a background assumption in almost every sentence. If distance is often described as light travel time, what does that mean given this convention, and how much of it is measurement versus coordinate choice? A light year is defined using c and a year of time, and the definition is crisp enough to print in textbooks. It turns a time interval into a distance by multiplying by the constant, and the constant itself is anchored to round-trip procedures. In practice, astronomy grounds distances through geometry and round-trip methods where possible, because geometry does not need distant clocks. Radar ranging to planets is explicitly out and back, and the echo returns to the same receiver that sent it. Parallax is geometric and uses angles, not distant clock synchronization, and it is measured by watching a nearby star shift against a far background. Standard candles use brightness and models, not one-way timing, even though the language of light travel time remains tempting. Yet the language of light travel time remains central because observation is reception, and reception is local. Telescopes record arrivals here and now, then infer emission there and then, and the inference needs a consistent time coordinate to stay coherent. To speak consistently about then, across space, cosmology adopts a time coordinate, and that coordinate is a choice of slicing. It chooses a way to slice space-time into moments, and the slices become the stage on which history is narrated. In flat space-time, Einstein's synchronization provides that slice for inertial frames, and it makes the slice look like a clean stack of parallel planes. In curved space-time, the slicing becomes more complex, but the need remains, because you still must decide what counts as at the same cosmic time. So the mystery is not a loophole that breaks measurement, and it is not a secret that lets physics evade accountability. It is a reminder that measurement includes definitions, and definitions are the scaffolding that lets data become statements. Light speed is both a measured fact and a chosen language, and the two are intertwined in practice. We measure the round-trip constant, then choose how to define now at a distance, and the choice becomes the grammar of every one-way sentence. That choice is what makes one-way speed meaningful, and it is what makes distant timestamps comparable. It is also what lets us build maps of the universe that turn distance into time, and time back into distance, without collapsing into contradiction. Next, we will test the edges of this convention. We will ask what experiments can actually constrain, and what they can never touch directly, even in principle. We will also connect the convention to the light year's power as a ruler, because the ruler is made from a clock. The universe is mapped by light, and light turns distance into time. We ended with a boundary that better instruments cannot erase, because the one-way speed hides behind how we define a distant now. Even if your clocks are atomic and your lasers are pristine, you still face a quieter problem. To time a one-way trip, you need 2 clocks separated in space. You must also decide what it means for those clocks to agree right now, across a distance. Special relativity enters as a bargain, not a decoration on old physics, and the bargain is paid in the currency of simultaneity. It keeps the speed of light invariant, and it charges us absolute simultaneity. That trade sounds philosophical until you try to build an experiment. Then it becomes operational, because every timing procedure smuggles in a rule for synchronizing clocks. Einstein's first postulate sounds modest, until you push it into corners where intuition used to hide. The laws of physics look the same in every inertial frame, with no preferred uniform motion. Inertial here means unaccelerated, coasting without forces that you can feel. It is the idealized state of a lab drifting in deep space, far from engines and gravity. The second postulate is sharper and stranger in practice, because it gives light a special status among signals. Light in vacuum has the same speed c for all inertial observers, regardless of source motion. Not almost the same, and not the same on average, but the same in a way that survives changing frames. That is why it collides with everyday velocity addition, where speeds simply stack. Taken together, these postulates do not merely fit electromagnetism, and they do not merely tidy up Maxwell's equations. They rewrite how space and time must transform between observers who disagree about motion. If everyone measures the same c, then time cannot be a universal background tick. Space cannot be a rigid stage either, because distances and durations must adjust together. The documentary hook tightens here, because the constant we celebrate also exposes a measurement wound. We teach c as the ultimate constant, yet one-way speed still depends on how clocks share a definition. The two-way speed can be checked with one clock and a mirror. The one-way speed demands a network of clocks, and a rule for what simultaneous means across that network. Before Minkowski diagrams, the crisis was framed as an ether problem, and the ether was imagined as a physical substance. If light were a wave in a medium, motion through that medium should show up. 19th century physics had waves on strings and waves in water, and it was natural to picture light similarly. The ether would be the invisible ocean, filling space and giving light something to ripple through. Michelson and Morley build an interferometer to catch that motion, and the device is deceptively simple on the page. They split a beam, send the halves down perpendicular arms, and recombine them to form interference fringes. The fringes are a ruler made of light itself, sensitive to path differences far smaller than a wavelength. In the lab, mirrors gleam, the beam splitter sits at a precise angle, and the pattern trembles with every vibration. They compare light travel times along perpendicular arms, then rotate the apparatus, watching for a shift that would betray an ether wind. If Earth moved through an ether, the fringe pattern should shift with orientation. One arm would face the wind, the other would cut across it, and the round-trip times would differ. The expected shift was not seen within the experiment's sensitivity, even as the heavy stone table turned. The null result is often simplified into a slogan, as if it directly measured light's one-way speed and found it unchanged. What it really constrains is anisotropy in the two-way speed, not a one-way timestamp. The interferometer is a closed-path machine, because both beams leave and return to the same place. It compares phases at reunion, and phase is a round-trip bookkeeper. Later tests close loopholes that the simple story leaves open, and they do it by changing what is held fixed. They do not just repeat Michelson, Morley, they change the logic of what is compared. Some vary the arm lengths, some vary the lab's velocity, and some use moving atoms as internal clocks. Each experiment tightens a different screw on the same symmetry. Kennedy and Thorndike keep the interferometer arms unequal, which makes the device sensitive to a different kind of failure. They watch for changes as Earth's speed through space varies across the year. The planet's orbital motion changes the lab's velocity relative to any hypothetical preferred frame. If c depended on the lab's velocity, the unequal arm device would drift in phase. The drift was not observed beyond tight bounds, even as seasons turned. Ives and Stilwell attack from a different angle, using moving atoms as clocks rather than relying on macroscopic arms. They measure relativistic Doppler shifts and confirm time dilation's factor. In their setup, fast ions emit light with frequencies that shift depending on motion. The key is the transverse Doppler effect, which is not just classical wave compression. It is a direct signature of time dilation, because the moving atom's internal rhythm slows in the lab frame. Together, these experiments do not hand us a one-way stopwatch reading, and that is the point worth lingering on. They confirm Lorentz symmetry and the invariant structure that makes C central. They show that nature behaves as if space-time has a specific geometry. Yet the experiments themselves mostly avoid the need to declare what time it is at a distant location. This is the key distinction that keeps the mystery alive, even in an era of exquisite precision. Experiments overwhelmingly test closed paths, resonances, and frequency comparisons that return home. A beam goes out and comes back, or a standing wave fits an integer number of wavelengths. The apparatus can be read at one location by one clock, with no dispute about simultaneity. Relativity's claim is not that every observer sees the same coordinate times, because coordinates are a choice. It is that the laws keep their form, and light's causal role stays fixed. The equations of electromagnetism do not break when you change frames. The maximum signal speed that protects cause and effect remains the same boundary. To see the price, we have to talk about simultaneity as a physical question, not a mere linguistic convention. It sounds like grammar, yet it controls what counts as a measurement. When you say two distant events happened at the same time, you're making a claim about how clocks are synchronized. that claim can be tested indirectly, because it shapes predictions about moving observers. Start with two events that feel obviously simultaneous, because the scene is built to flatter intuition. Two lamps flash at opposite ends of a platform, and a person at the midpoint watches. The platform is still, the lamps are identical, and the observer is centered. Visually, it looks like a fair experiment, balanced like a scale. In the platform frame, the midpoint observer sees the flashes arrive together, and that arrival is a single observation at one place. Under Einstein's synchronization, that implies the flashes happened at the same time. The rule is simple. If light from two ends reaches the midpoint simultaneously, then the emissions were simultaneous in that frame. It is a definition, but it is also a definition that meshes with the postulates. Now put a second observer on a train moving past the platform, and keep the flashes the same physical events. That observer is not at rest with the lamps, and the geometry shifts. The train slides through the scene, steel and windows passing the platform edge. The observer's world line is tilted in the platform diagram even before we draw it. The train observer moves toward one flash, and away from the other, so the light has different distances to chase. Light from the forward end meets the observer sooner than light from the rear end. This is not because light changes speed, but because the meeting points are different. The observer's motion changes where the light catches them. If the train observer receives the flashes at different times, the train cannot keep the platform's simultaneity. The observers must disagree about which flash happened first. If they tried to force agreement, they would break the invariance of C or distort the symmetry of the laws. The disagreement is not optional, because it is built into the consistent transformation rules. This is not a trick of perception, and it is not a delay in the eye or in neural processing. It is a statement about how time coordinates must be assigned consistently. Each observer can correct for signal travel time in their own frame. Even after those corrections, the frames still disagree about simultaneity, because simultaneity is a frame-dependent slice through space-time. Space-time diagrams make the disagreement explicit without arguing about psychology, and they do it with almost austere clarity. Events become points, world lines become paths, and light becomes a 45-degree boundary. The diagram is not a picture of space, but a map of relationships. It tells you what can influence what and what cannot, given the speed limit. Draw the platform's time axis straight up and its space axis sideways, and the grid becomes a calm reference. Light rays trace diagonals, and the midpoint observer sits on a vertical line. The lamps are fixed at 2x positions, and their flashes are points on those vertical world lines. The arrival at the midpoint is another point, where two diagonals meet the observer's line. Now draw the train's axes tilted relative to the platforms, and the page begins to show the bargain. The tilt is not artistic, it is the Lorentz transformation drawn as geometry. The train's time axis leans toward the direction of motion, because time for the train is aligned with its world line. The train's space axis leans the other way, because simultaneity lines must remain consistent with the light cone. Lines of constant time for the train are slanted across the platform's grid, cutting through events differently than the platform's horizontal lines. That slant is the loss of absolute simultaneity made visible. What one frame calls now is not parallel to what another frame calls now. The difference is small at low speeds, which is why daily life hides it so well. The key object is the light cone, which divides space-time into regions with different causal meaning. Inside the cone, signals can connect events, and outside it, they cannot. The cone's surface is traced by light itself, defining the ultimate boundary. No matter how you tilt coordinates, the cone remains the same shape because C is invariant. Events outside each other's light cones are space-like separated, and that phrase is more than jargon. Their time order can flip between inertial frames without creating any causal contradiction. If no signal can travel between them at or below C, then which happened first cannot be used to send a message. The universe protects causality by making the flip physically harmless. That flip is the heart of the bargain, and it is why relativity feels unsettling at first contact. Relativity allows different slices of now, while protecting the boundary that prevents cause from outrunning light. The protection is not a moral rule, it is a geometric one. It is encoded in the invariant interval that all inertial observers agree on. The protection comes from an invariant quantity, not from a preference for any frame, and that is what makes the theory so rigid. The space-time interval stays the same for all inertial observers. It plays the role that distance plays in ordinary Euclidean geometry. Rotate your axis on a sheet of paper, and the distance between 2 points does not change. In Minkowski's language, space and time form a single, four-dimensional structure, and the union is not merely poetic. Different observers rotate their axes through space-time, not through space alone. The rotation is hyperbolic rather than circular, because time enters with a different sign. That sign difference is what keeps the light cone fixed while allowing time and space to mix. The interval is written as c squared times delta t squared minus delta x squared, with the sign convention carrying the causal meaning. If the interval is time-like, all frames agree on order. If it is light-like, all frames agree that light could connect the events. If it is space-like, frames may disagree on order, and causality remains unthreatened. Lorentz transformations are the bridge that makes this work, and they are more constrained than they first appear. They replace Galilean addition of velocities with a mixing of space and time coordinates. The mixing is controlled by the factor gamma, built from v squared over c squared. As v approaches c, gamma grows, and the mixing becomes dramatic. They are not optional patches to save c from contradiction, and they are not a clever algebraic trick. They are the unique linear transformations that preserve the interval and keep light on the same cone. Linearity matters because inertial motion maps to straight world lines, and straightness is preserved. Once you demand those features, the Lorentz form is essentially forced. From the transformations fall the famous effects, now as bookkeeping consequences rather than isolated miracles. Time dilation and length contraction are not separate laws, they are geometry. They describe how different coordinate grids slice the same space-time. The effects are reciprocal between inertial observers, which is why they cannot be explained by a simple physical slowing mechanism. A moving clock accumulates less coordinate time in a given frame, and the statement can be made precise. The clock's proper time is the time along its world line, the time it actually experiences. In a diagram, proper time is tied to the interval, not to any chosen coordinate. That is why it is invariant, even when coordinate times differ. A moving rod measures shorter along the direction of motion in that same frame, and the contraction is tied to simultaneity. To measure a length, you must mark both ends at the same time in your frame. Change the definition of same time, and you change which pair of events counts as the endpoints. The contraction is not a crushing force, but a difference in slicing. These effects are often taught as surprises, yet they are the cost of invariance, paid consistently across all measurements. If c is fixed for all inertial observers, then simultaneity cannot be fixed too. You cannot keep both without contradiction, because a universal simultaneity would reintroduce a preferred frame. The bargain is that no frame gets that privilege. This returns us to the one-way measurement problem with new force. One-way speed needs distance simultaneity, and relativity says distance simultaneity is frame-dependent. You can still define a one-way speed, but the definition will carry the fingerprint of your synchronization choice. That fingerprint is invisible in many experiments because they never require distant clock agreement. Einstein's synchronization becomes more than a convenience because it is built to respect the postulates cleanly. It is the convention that makes light's one-way speed equal to c in each inertial frame. You send a light pulse from A to B and back, and you set B's clock so the outbound and inbound times split evenly. The procedure uses only a round trip, yet it defines a one-way coordinate speed. Change the convention, and the coordinate one-way speeds can change, even though no local physics changes. The two-way speed stays c, and the light cone structure stays intact. The difference shows up in how you label distant events, not in what can be caused or detected locally. That is why the issue feels slippery, like a shadow cast by definitions. That is also why the experiments in the real world keep circling back to round trips, because round trips avoid the definitional trap. They test the invariants that do not require a global now. A single lab can compare phases, frequencies, and arrival times at one location. The results can be shared without arguing about how to synchronize clocks across continents. Interferometers compare phases that reunite at one detector, and phase is a powerful witness. A tiny change in travel time becomes a measurable shift in fringes. Resonators compare frequencies of standing waves that are defined by closed paths. A cavity mode counts how many half wavelengths fit between mirrors, and the count is local. These devices are sensitive to anisotropy and to boosts, yet they do not need two separated clocks, and that is their advantage. They can test Lorentz symmetry without asking what time it is over there. The apparatus becomes a self-contained judge because the signal returns to the same place. The experimental question becomes, does rotation or motion change the beat note? Modern versions push the same logic to extremes, and the visuals become almost futuristic. Optical cavities are rotated, cryogenic resonators are stabilized, and frequency combs count cycles with precision. In a clean lab, vacuum chambers hum softly, and mirrors sit on vibration-isolated platforms. Lasers lock to cavity modes, and the readout is a narrow line on a spectrum analyzer. The observable is a beat note or a fringe shift at one location, and that locality is the methodological theme. The experiment asks whether orientation or velocity changes the round-trip behavior. If space had a preferred direction for light propagation, the cavity frequencies would drift as the Earth turns. If boosts mattered, annual changes in velocity would modulate the signal. This is why Michelson Morley has descendants rather than replacements, because the core idea remains structurally matched to clean measurement. The method is not old-fashioned, it is structurally matched to what can be measured cleanly. When you rotate a cavity or an interferometer, you are effectively scanning space-time symmetry with a compass made of light. The compass points not north, but toward invariance or its violation. Kennedy, Thorndike-style tests still matter because they probe boost dependence, and they do it without needing a preferred direction. The unequal arms make the device sensitive to changes in speed through space. Ives, Stilwell-style tests still matter because they probe time dilation directly, using atoms whose internal transitions act as stable oscillators. Together they triangulate the same underlying symmetry from different experimental geometries. Together they map the symmetry group that spacetime seems to obey, and the mapping is remarkably consistent. They confirm that the Lorentz transformations are not merely a mathematical taste. They also constrain many alternative theories that would allow tiny deviations. The message is not that every coordinate statement is absolute, but that the invariant structure is stubbornly real. Causality is the non-negotiable constraint that survives every coordinate choice, and it is the reason the bargain feels safe. No matter how you slice simultaneity, you cannot send a controllable signal outside the cone. You can relabel events, you can tilt axes, and you can choose conventions. You cannot build a device that makes an effect precede its cause in every frame. Relativity's bargain is therefore not a license for anything-goes physics, even though it loosens the grip of absolute time. It is a disciplined freedom in coordinates, sitting on top of rigid invariance. The interval, the light cone, and the form of physical laws are the anchors. The coordinate labels are the ropes, and different observers tie them differently. Minkowski spacetime is where the measurement issue meets the structure of reality, and the meeting is not abstract. The one-way question is not about photons alone. It is about the geometry of time. If time is part of a four-dimensional structure, then one way is not just a path in space. It is a path through spacetime, measured relative to a chosen slicing. In this geometry, a distant now is not a universal sheet, and it is not a cosmic drumbeat heard everywhere at once. It is a family of slices, each tied to an inertial frame's definition of rest. Each slice is internally consistent, and each respects the light cone. Yet different slices cut through the same set of events in different ways. That sounds local and technical until you scale it up, and then it becomes a quiet shock. If simultaneity is slippery even across a lab, it becomes a major issue across galaxies. The distances are immense, the travel times are long, and the only information we receive arrives on light. When we talk about what is happening now in a distant galaxy, we're already choosing a convention. Astronomy already speaks in light travel time because observation is reception, and the telescope is a receiver. Telescopes record arrivals here, then infer emissions there, using a chosen time coordinate. The photons do not carry a timestamp from the sources present. They carry a history of their journey, and we reconstruct the story with models and coordinates. On solar system scales, we can still anchor distance with round trips, and the procedure is almost comforting. Radar ranging sends a pulse and times the echo, keeping one clock in charge. The method is operational, and it avoids distant synchronization. A spacecraft becomes a mirror, and the Earth-based clock does the accounting. On stellar scales, we lean on geometry and models rather than echoes, because the echoes are too faint and too slow. Parallax uses angles, and standard candles use calibrated brightness, not synchronized clocks. We build a distance ladder, step by step, each rung anchored to a different method. The ladder is powerful, yet it is also a reminder that distance is inferred, not directly touched. Yet cosmology keeps translating distance into time because light is the messenger, and the messenger has a finite speed. The light year is not poetic, it is operational, and it encodes the bargain. It is a unit of distance defined by a unit of time and the invariant C. Every time we use it, we are quietly leaning on relativity's structure. If we say a galaxy is 1 billion light-years away, we are also saying we see it 1 billion years ago, in a specific coordinate sense. That statement depends on how we map space-time into a history. It is a statement about our past light cone, the set of events that can send light to us now. The galaxy's now is not directly observed, only its then. In an expanding universe, even the word distance splits into competing definitions, and the split is not pedantry. There is proper distance now, comoving distance, luminosity distance, and angular diameter distance. Each is built to answer a different observational question. One tells you how far something is at a chosen cosmic time, another tells you how brightness falls off, and another tells you how big it looks. Those distances are not contradictions, they are different ways to slice and project space-time, and the slicing echoes the simultaneity issue. Each choice answers a different question about observation and evolution. When you change the definition, you change the mapping between redshift, time, and distance. The universe does not become inconsistent, but our bookkeeping changes. Special relativity does not solve cosmology, yet it sets the rules of the local game, and cosmology must respect those local rules. It tells us that time coordinates are constructed, and only invariants are shared. Locally, physics looks Lorentz invariant to high precision. Globally, space-time can curve and expand, but the causal structure still leans on light cones. So the chapter ends with a widened mystery, not a closed one, because the bargain scales with us. If now is not absolute even in flat space-time, cosmic now will be a careful choice. The question is not whether we can define it, but what we pay when we do. What becomes simple, and what becomes ambiguous, when we select one slicing over another. Next, we take this bargain into the expanding universe. We will ask how cosmology defines time, distance, and horizons when light is the only surveyor. We will watch how redshift becomes a kind of clock, and how horizons become boundaries of knowledge. The same insistence on invariance will guide us, even when the geometry is no longer flat. And we will keep the central question in view, because it is the thread tying measurement to meaning. If one-way speed depends on now, then mapping the cosmos in light years is not a workaround, it is the honest method. It admits what we can directly observe, and it respects the causal boundary that no instrument can erase. The bargain remains, and the universe keeps its secrets within the cone. Special relativity gave us a clean bargain in flat space-time, where inertial frames can stretch across a lab and still agree on what straight means. General relativity begins by breaking that comfort, because gravity is not a force pasted onto space and time. Gravity is the geometry of space-time itself, and geometry can vary from place to place, even from moment to moment. In special relativity, you can imagine one global grid for an unaccelerated observer, then compare other grids by Lorentz transformations that preserve the space-time interval. The picture is crisp. Rulers and clocks can be idealized as if the background never changes. In general relativity, that global inertial grid does not exist in any extended region with curvature, because the metric itself carries information about gravity. You can always find a local inertial frame at a point where physics looks special, relativistic, and freely falling objects momentarily behave as if no gravity exists. But as you move away, tidal effects reveal the truth. Nearby geodesics converge or diverge, and the straight lines of one patch do not stay straight. Visually, think of a finely drawn lattice floating in darkness, each square representing a unit of space, and each tick a beat of time. In special relativity, that lattice can tilt, but it stays uniform and unwrinkled across the whole scene. In general relativity, the lattice buckles near mass and energy, and the spacing between ticks subtly changes, as if the grid were printed on a flexible fabric. The effect is not merely artistic because the curvature shows up in measurable ways, like the stretching and squeezing that produce tides. This matters for the documentary's central question, because the one-way speed problem was already about coordinates and now. In curved space-time, coordinates become even more openly a choice, and the universe does not hand you a universal time label that every observer must share. Instead, it hands you clocks on world lines, each measuring its own proper time, and light cones that limit what can be compared. When two events are far apart, the question, which happened first, can depend on how you slice space-time into moments. General relativity replaces the idea of gravitational pull with geodesics, the straightest possible paths in curved space-time, defined by the metric rather than by intuition. Matter and energy tell space-time how to curve, in equations that relate geometry to stress energy. Curvature tells matter and light how to move, not by pushing them, but by shaping the paths that count as inertial. Light still follows null paths, and locally its speed is still c, but the global story of travel time becomes geometry rather than simple kinematics. So the chapter's pivot is not just bigger distances, or a larger map drawn with the same ruler. It is a new kind of ruler, one that can bend, stretch, and even evolve while you are measuring with it. When space-time itself changes, distance is no longer a single number you read off a static background, because the background is part of the phenomenon. We now shift from local space to cosmic space, where the universe becomes the coordinate system. Cosmology assumes that on large scales the universe is homogeneous and isotropic, at least statistically, even though it is clumpy in detail. That symmetry is not a philosophical preference, and it was not adopted because it feels aesthetically pleasing. It is an empirical summary of galaxy surveys, the distribution of clusters and voids, and the near uniformity of the cosmic microwave background. Historically, this shift was not instantaneous, because early 20th century astronomy was still arguing about the scale of the cosmos. When Hubble and others established that spiral nebulae were external galaxies, the universe became a realm with structure on unimaginable scales. Soon after, relativistic cosmology developed a language to describe expansion without placing Earth at the centre. The modern assumption of large-scale uniformity is a hard-won simplification, tested again and again as surveys grew deeper. Those symmetries lead to a standard spacetime model, the FLRW metric, which is general relativity written for an expanding cosmos with a smooth cosmic fluid. The key ingredient is the scale factor, AIT, a function of cosmic time that multiplies spatial distances in the commoving grid. It tells you how the size of the universe's spatial slices changes with time, and it encodes the expansion history we infer from the sky. Expansion is not galaxies flying through space like shrapnel from an explosion, because the image suggests a center and a pre-existing emptiness. Expansion is the stretching of the spatial geometry between comoving world lines, while local systems remain bound by their own gravity. To make that idea visible, imagine points of light suspended in a transparent lattice, with faint lines connecting them like a three-dimensional graph. As time advances, the lines lengthen, yet the points do not accelerate through the lattice, because the lattice itself is what is changing. In the background, the cosmic microwave background can be shown as a soft, nearly uniform glow, a kind of cosmic wallpaper that defines the large-scale rest frame. The scene communicates a subtle claim. The coordinate system is not imposed from outside, but built from the universe's own symmetries. Comoving coordinates are the bookkeeping that makes this picture usable, because they label galaxies that ride with the expansion. A comoving galaxy keeps the same spatial coordinates as the universe expands, provided it is not in a bound structure like a cluster core. Its proper distance changes because AT changes, not because it is locally accelerating through space in the everyday sense. The Hubble flow is the collective recession of comoving observers, described by VHT, d for small enough distances, where HT is the Hubble parameter at that epoch. That relation is not a special relativistic velocity law, and it is not a claim that objects break the speed of light in their local neighbourhoods. It is a statement about how proper distance changes with cosmic time, which can exceed c without violating local causality. This is where tension builds, because the word distance starts to split into several legitimate meanings. In a static Euclidean world, distance is a single geometric fact, and time can be treated as a universal parameter for the whole map. In an expanding curved space-time, distance depends on which slice of time you mean, and on which operational question you are answering. Even the act of defining at the same time across the cosmos becomes a modelling choice, guided by symmetry and by what observers can actually measure. Proper distance is the length of a spatial path at a chosen cosmic time, measured along the spatial slice defined by that time coordinate. It answers the question, how far is that galaxy right now in this cosmic slicing if we imagine freezing the expansion on a single hypersurface, but right now is already a coordinate choice, and in general relativity different slicings are possible, each with its own notion of simultaneity. Fellablu picks a natural slicing tied to the symmetry of the cosmic fluid, because co-moving observers see the universe as isotropic on average. Co-moving distance factors out expansion by dividing proper distance by AT, which turns changing separations into fixed coordinate labels. It is the distance in the coordinate grid that expands with the universe, and it stays fixed for co-moving objects in the Hubble flow. That stability makes it useful for large-scale structure, because it lets us compare where features are in the cosmic web without constantly rescaling the map. It answers a different question. Where is the galaxy in the expanding map, independent of the universe's current size? Then observation forces a deeper fracture, because telescopes do not measure proper distance directly, and they do not reach out with meter sticks. Telescopes measure flux, angles, spectra, and redshift, all filtered through instruments and through the intervening universe. Those observables translate into distances only through models of space-time and expansion, and through assumptions about how light propagates on large scales. The sky gives us photons and statistics, not a ruler laid end to end. Luminosity distance is defined so that the inverse square law keeps its familiar form F L 4PD DEL2, even when the universe is not static. In an expanding universe, photons lose energy to redshift because their wavelengths are stretched along with space, and they arrive less frequently due to time dilation in the source's light curve. Those effects make objects dimmer than a static Euclidean distance would predict, even if no dust exists. Luminosity distance packages that dimming into a single number, even though it is not a simple geometric length you could measure with a rigid rod. Angular diameter distance is defined so that an object's physical size relates to its observed angle, the Biast size dA, which makes it the natural distance for standard rulers. In Euclidean space, farther objects look smaller in a monotonic way, and the relationship feels almost self-evident. In cosmology, dA can increase, and then decrease with redshift, making very distant objects appear larger again in angular terms. That behavior is not an illusion, and it is not a trick of the telescope. It is the geometry of light propagation through an expanding space-time, where the bundle of light rays can be focused and defocused by the expansion history. Co-moving distance, proper distance, luminosity distance, and angular diameter distance are not competing truths, and they are not a sign that cosmologists cannot agree on definitions. They are different projections of the same space-time onto different measurement tasks, each tuned to a specific operational question. The same galaxy can have several distances at once, each correct in its own definition, because each definition answers a different how far question. The fracture is not pedantry, it is the cost of mapping a dynamic geometry with light. This connects back to the earlier chapter's theme because distance equals light travel time is also a convention-laden statement. In special relativity, one-way timing depended on how we defined simultaneity between separated clocks, and that dependence was not a minor technicality. In cosmology, we rarely synchronize clocks across galaxies because we cannot exchange signals back and forth on human timescales. We infer times and distances from light received here, using a chosen cosmic time coordinate and a model of how the universe evolves. Cosmic time is the time measured by observers who ride with the Hubble flow, seeing the universe as isotropic on large scales. In the FastW model, cosmic time labels the homogeneous slices of the universe, like pages in a book where each page is a snapshot of the cosmic fluid. It is not the proper time of every observer, because moving observers and deep gravitational wells tick differently, and general relativity insists on that difference. It is instead a practical standard time for the cosmological map, chosen because it aligns with the universe's large-scale symmetries. But why believe such a time is more than a mathematical convenience, like a coordinate trick that could be swapped out without consequence? Because the universe provides a physical reference that is close to unique, and it announces that reference in the oldest light we can see. The cosmic microwave background defines an almost universal rest frame, because it is the relic radiation from the early universe, now cooled to microwaves by expansion. If you move relative to it, the CMB temperature shows a dipole anisotropy, hotter in the direction of motion and cooler opposite, like the wind chill of motion through a sea of photons. That dipole is measured with exquisite precision, and it tells us the solar system is moving at hundreds of kilometers per second relative to the CMB frame. The pattern is not a vague trend, but a clean signal extracted from maps that also contain tiny primordial fluctuations. This does not resurrect an ether, because local physics remains Lorentz invariant, and no local experiment finds a preferred direction for C. It does give cosmology a practical notion of rest, tied to the matter radiation distribution of the universe and to a specific observational signature. So the story becomes layered, with two kinds of no preference living side by side. Locally, there is no preferred inertial frame, and the one-way speed remains tied to synchronization conventions and coordinate choices. Globally, the universe's matter content defines a natural co-moving frame, and the CMB lets us identify it operationally with a thermometer in the sky. The tension is not a contradiction, and it does not undermine relativity's core claim. It is the difference between local symmetry and global structure, between what holds in a neighborhood and what emerges across billions of light years. Now the chapter tightens around the word distance, because cosmology uses redshift as a primary observable, and redshift is written directly into spectra. When a spectrograph spreads starlight into a barcode of lines, those lines arrive shifted, as if the universe had stretched the ruler printed on the light itself. Redshift is not just a Doppler effect from motion through space, though Doppler language can be useful at low redshift. In the FLRW picture, redshift is largely the stretching of photon wavelengths by expansion, 1 plus z A now, A then, which ties observation to the scale factor's history. Once redshift becomes the handle, distance becomes model-dependent in a controlled way, and the dependence is not arbitrary. Given a cosmological model, you can integrate the expansion history to convert z into co-moving distance, accounting for how fast the universe was expanding at each epoch. You can then derive DLL and dA and compare them to supernova brightness or galaxy angular scales, checking whether the same model fits everything at once. The map is consistent when the model is consistent, and inconsistency shows up as mismatched curves rather than as philosophical discomfort. But the documentary's mystery returns in a new form, because even if we accept cosmic time and co-moving coordinates, light travel time is not a simple ruler in an expanding universe. A photon does not cross a fixed distance at speed c through a static space. Like a bullet crossing a range, the space it traverses changes while it travels, and the metric that defines distance is evolving as the photon moves. The path is still null, and locally the photon still moves at c, yet the global bookkeeping of how far becomes a story of the universe's changing scale. Look-back time is the difference between the universe's age now and its age when the light was emitted, computed in cosmic time for the co-moving frame. It is a time, not a distance, though we often translate it into light years in casual speech because the conversion feels intuitive. That translation can mislead, because the proper distance to the source now can be much larger than c times the look-back time. Expansion means the separation grew while the photon was en route, so the distance now and the travel time then to now are not interchangeable. To picture this, imagine a photon as a bright bead sliding along a wire, while the wire itself is being stretched by invisible hands. The bead never exceeds its local speed limit, yet the endpoints can separate so dramatically that the final gap is larger than the bead's travel time suggests. The image is imperfect, but it captures the essential surprise. The ruler is not rigid, and the map is not frozen. This is where the phrase, "How far away is that galaxy?" becomes a trap, because the question hides multiple meanings behind one familiar word. You can mean the proper distance now, on today's cosmic time slice, which is a snapshot distance. You can mean the proper distance then, at emission, which is the separation on a past slice of cosmic time. You can mean the co-moving distance, which stays fixed for the Hubble flow and acts like a coordinate address. You can mean the luminosity distance, which matches brightness and photon dilution. You can mean the angular diameter distance, which matches apparent size and the focusing of light bundles. Each answer can be numerically different, even for the same object, even in the same cosmological model, and the differences can be large at high redshift. The fracture is the chapter's central tension, because it forces us to admit that, distance is not a single operational question. The universe refuses to give a single distance because the act of measuring is inseparable from the geometry and from the time slicing. What we gain is not confusion, but a richer vocabulary that matches what the sky actually offers. This also reframes the earlier promise to test the edges of synchronization freedom. In a lab, Reichenbach's epsilon freedom changes one-way assignments while leaving round-trip results fixed, and the ambiguity lives inside the coordinate choice. In cosmology, we do not even attempt one-way timing with distant clocks, because we cannot send a signal and get an answer back within a meaningful time frame. We build a coordinate time from symmetry and from the CMB rest frame, then compute distances from redshift and light propagation within that framework. So what constrains the choice, if not a direct one-way measurement across intergalactic space? Not a single privileged experiment, but consistency across many observables that sample different epochs and different physical processes. The same FLRW model must fit supernova-like curves, baryon acoustic oscillations, CMB anisotropy patterns, and galaxy clustering, even though each probe has its own systematics. If your coordinate choices or distance definitions break those links, the map stops matching the sky, and the mismatch cannot be hidden by clever language. That is the cosmological version of an empirical constraint, and it has a different flavor than the constraints in flat spacetime. It does not pick a unique simultaneity convention in special relativity, because local Lorentz symmetry still allows that freedom. It does pick a practical cosmic slicing that makes the universe's large-scale data coherent, because the data themselves are organized by the universe's near uniformity. It is a selection by usefulness and symmetry, backed by cross-checks that span billions of years and enormous volumes. Now we can explain why light years become the honest language, even when they are subtle and easy to misuse. Light is not just a messenger, and it is not merely a convenient signal we happen to detect. It is the only messenger that reaches us from most of the universe, and it carries information in time order along our past-like cone, one arrival after another. The universe does not show us distant places as they are now, in any absolute sense, because now is not something the cosmos broadcasts. It shows us distant events as they were when their light began the journey. A mile is a local unit tied to rods, surveys, and the assumption that space can be treated as stable across the measurement. A light year is tied to the causal structure that actually connects us to distant events, and it is defined through the behavior of light itself. When we say a galaxy is billions of light years away, we are admitting that the measurement is mediated by light and by time, not by direct reach. We're also admitting that the universe's geometry is part of the ruler, because the light's path is shaped by expansion. Yet even the light year must be handled carefully in cosmology, because it can quietly smuggle in an implied definition of distance. If you mean look-back time in years, you're describing when the light was emitted in cosmic time, which is a statement about history. If you mean a distance in light years, you must say which distance definition you're using, because the same redshift can correspond to different light-year numbers depending on what you mean. Without that, the number can be correct and still answer the wrong question, like giving the right temperature in the wrong units. The chapter ends by returning to the hook, now expanded into cosmic scale and cosmic patience. We celebrate C as a constant, and we measure it with round trips and local clocks, where the geometry is nearly flat and the rules feel familiar. But the universe is mapped by one-way arrivals, photons that never return, and by patterns in their spectra and brightness. To turn those arrivals into distances, we must choose a time coordinate, a slicing, and a definition of distance that matches the measurement we are actually making. In special relativity, the ambiguity lived in synchronizing clocks across space, because one-way timing requires a convention. In cosmology, the ambiguity lives in choosing a cosmic now, and deciding which distance you mean, because the universe is evolving while the light travels. The one-way mystery does not disappear, and it does not become a mere footnote. It becomes the method, an invitation to be explicit about what our questions really ask. Next, the story moves from distance definitions to boundaries, where expansion and light speed create horizons. We will ask what parts of the universe are in principle observable, and what parts are separated by geometry itself. We keep calling the light-year poetic as if it belongs to metaphor, yet astronomy treats it as a working tool. Astronomers use it because information arrives at light speed and distance becomes a time problem we can actually observe. When we point a telescope outward, we are not sampling space directly. We are sampling arrival times, energies, and directions of photons. A light year is a unit of distance, not a unit of time, and that distinction matters for clear thinking. It is the distance light travels in 1 year, about 9.46 trillion kilometers, or about 5.88 trillion miles. That number hides a constant we lean on. In vacuum, light moves at about 299,792 kilometers per second, and it does so with extraordinary reliability. That definition can sound like a conversion trick, yet it matches the universe's operating system in a literal sense. Across interstellar and intergalactic space, light is the courier for almost every measurement, because it is what survives the trip. Grains of dust, charged particles, and even neutrinos play roles, but for mapping the sky, photons carry the bulk of the usable detail. Miles and kilometers still work mathematically, yet they stop working cognitively once the zeros dominate the page. The numbers become so large that they hide the method, and the method is the real story. A unit that keeps travel time visible keeps causality visible, and causality is the thread that holds the map together. A telescope never reaches out and touches a galaxy, no matter how large the mirror becomes. It waits for photons to arrive, then reconstructs where and when they were emitted from patterns in those arrivals. Even the act of focusing is a kind of negotiation with geometry. Angles on the sky are translated into a picture by optics, detectors, and calibration. This returns us to the documentary's central question about one-way light speed. In the lab, one-way timing needs synchronized clocks, and synchronization quietly defines a distant now that can never be checked without assumptions. You can measure a round trip cleanly with one clock, but a one-way claim smuggles in a convention about simultaneity. In astronomy, we rarely even pretend to synchronize clocks with a star, because we cannot send a timing signal and demand a reply. We accept that we receive one-way arrivals, and we build distance from what those arrivals encode in brightness, color, and timing. The sky becomes a record of received messages, not a set of objects sharing our present tense. The sky is not a window into the present, even when it feels immediate to the eye. It is a layered archive of past light, stacked by travel time along our past light cone. Every pinpoint star is a timestamp, and every faint galaxy is a deeper timestamp, arranged across the dome of the sky like pages scattered in the dark. Look-back time is the cleanest statement we can make without touching conventions too hard. When we see a galaxy at high redshift, we see it as it was, not as it is right now. The photons left when the universe was younger, when galaxies were assembling, and when star formation followed different rhythms. That is not a philosophical flourish, and it is not optional if we accept that light has a finite speed. The finite speed of light forces every observation to be delayed information, and delay is a physical constraint. Even if we never mention relativity, the delay is already a causal boundary between what can influence us now and what cannot. Even nearby space teaches the lesson in a gentler form, as if the universe is offering a rehearsal. Sunlight is about 8 minutes old when it warms Earth, and that delay is already a boundary between cause and effect. If the sun changed suddenly, Earth would continue under the old sunlight for minutes, because the news can only arrive at sea. At cosmic scales, the delay becomes the map rather than a footnote. 1 billion light years is not just far, it is 1 billion years of travel time encoded in arriving photons. When we say the number aloud, we are really saying how long the universe has been carrying that message toward us. Yet the documentary's tension deepens here, because time and distance are not identical in cosmology. The universe expands while the light travels, and the ruler changes mid-measurement as space itself evolves. The light year keeps the travel time intuitive, but it does not freeze the geometry in place, so we need a language that keeps the operational truth visible, without pretending the cosmos is static. Light-time units keep the method on the surface, even when the geometry underneath is evolving. They remind us that we never observe distance now directly, we infer it through models that connect emission to reception. Astronomy turns light into distance by building a ladder, not by making one giant measurement across the void. Each rung is calibrated by the rung below, and each rung relies on a light behaving consistently. This is one reason the history of astronomy is also a history of calibration, of learning how to trust numbers by tying them to other numbers. The first rung is parallax, which is pure geometry, and almost disarmingly simple in concept. As Earth moves around the Sun, nearby stars shift against the distant background by a tiny angle. The effect is the same depth cue your brain uses, except the baseline is an orbit nearly 300 million kilometers wide. Measure that angle carefully, and you infer distance without guessing the star's physics or its brightness. The baseline is Earth's orbit, and the observable is a change in direction measured against faraway reference stars. Historically, the first successful stellar parallaxes in the 19th century were a triumph precisely because they turned how far into a measurable angle. Parallax is powerful, yet it is limited by small angles and instrument stability, and those limits are unforgiving. Beyond a certain range, the shift becomes too tiny, and the ladder must climb. A parallax of 1 arcsecond defines a parsec, and even that angle is so small it is like seeing a coin from kilometers away. Modern astrometry missions sharpen this rung dramatically, and the visuals reflect that precision. Imagine a star field where positions are tracked over years, dots sliding by fractions of a pixel as the spacecraft's detectors count photons. The measurement is not one snapshot, but a choreography of repeated observations corrected for motion, distortion, and the telescope's own subtle flexing. The next rung uses Cepheid variable stars, which are not standard candles by accident or by wishful thinking. Their pulsation period correlates with their intrinsic luminosity through the period. Luminosity relation, discovered through patient sky surveys. The physics is rooted in stellar structure, layers of ionized helium trap and release heat, driving rhythmic expansions and contractions. A Cepheide's brightness rises and falls with a regularity that can be timed, and time becomes the key. If you know a Cepheide's true luminosity, you can compare it to its apparent brightness as seen from Earth. The dimming tells you distance through an inverse square law corrected for dust absorption and for the detector's wavelength band. But you must calibrate that luminosity first, and parallax provides the anchor that keeps the rung from floating away. The ladder is not a metaphor. It is a chain of dependencies, and a weak link corrupts everything above it. That is why astronomers obsess over systematics, dust, metallicity, crowding, and detector calibration, because small biases can masquerade as cosmic truths. Cepheids extend the map to nearby galaxies, where parallax no longer reaches with practical precision. They let us place galaxies on a distance scale tied back to geometry, which is as close to direct as astronomy can get. In a visual sequence, we move from a star's tiny wobble to a galaxy's spiral arms, and the same logic still holds. Light arrives, we decode it. Then the ladder climbs again with Type Ia supernovae, which are bright enough to be seen across much of the observable universe. They are standardizable candles, not perfectly standard ones, and that nuance is crucial. Their usefulness comes from patterns in their light curves and spectra that let us correct for differences. A Type Ia supernova comes from a white dwarf catastrophe, and its violence is as precise as it is spectacular. In many scenarios, a white dwarf gains mass from a companion or merges with another white dwarf, approaching conditions where runaway thermonuclear burning can ignite. For a brief time, it can outshine an entire galaxy, turning a single point of light into a cosmic beacon. Its light curve shape correlates with peak brightness, and that correlation is measured, not assumed. By fitting the curve, we infer the intrinsic luminosity and then distance, with corrections that account for colour and dust. The data look like a rising flare and a measured decline, points on a graph that become a distance when interpreted through calibrated physics. Cepheids calibrate Type Ia distances in galaxies that host both, and those rare overlaps are precious. That cross-calibration is the ladder's critical handoff, and it sets the scale for cosmic expansion measurements. You can picture it as two rulers overlapping by a few centimeters, letting you extend the measurement into a range neither could reach alone. Every rung is light-based, and every rung is indirect, even when the inference is tight. We infer distance from angles, brightness, and time-varying light, not from a tape measure in space. The universe gives us photons and geometry, and we build the rest by disciplined comparison. The method also inherits the earlier chapter's lesson about conventions, which lurk beneath every obvious distance. We do not measure a one-way speed across the cosmos. We interpret one-way arrivals using a chosen cosmic time slicing. The data are real, but the translation into a global picture uses a coordinate language we agree to speak. Even when the data are clean, the mapping is model-laden, because cosmology connects redshift, time, and distance through an assumed expansion history. The ladder tells us relative distances, Then cosmology turns those into a global picture with parameters. Those parameters are not arbitrary, but they are not delivered by a single measurement either. Now the story shifts from candles to spectra, where the universe writes distance into wavelength. Redshift is the most pervasive cosmic observable because it is stamped into every spectral line like a barcode. When we spread a galaxy's light into a rainbow, dark absorption lines and bright emission lines appear at specific wavelengths, and their displacement is the clue. At low redshift, the Hubble, Lemaitre law links redshift to distance through recession. The relation is approximately linear for nearby galaxies, and it becomes the first-order cosmic ruler. Historically, this was a turning point, because it reframed the universe from a static stage into a dynamic expansion. In that low-z regime, Doppler language is a useful approximation that matches intuition. Galaxies recede, lines shift, and the slope gives the Hubble constant, a number with units that quietly mix space and time. In visuals, the spectrum slides toward red as the galaxy's inferred recession increases, and the shift is measurable down to fractions of a nanometer. But cosmological redshift is not just motion through space, and the distinction matters as distances grow. In the expanding universe picture, wavelengths are stretched with the scale factor, and 1 plus z tracks that stretching. The photon's wavelength lengthens because the space it traverses is changing, and the shift accumulates continuously along the path. That stretching also dilates time in observed signals, which is a subtle but powerful confirmation. Supernova light curves appear broadened by a factor of 1 plus z, and that broadening is a direct observational fingerprint. The explosion is not physically slower at the source, but its time structure arrives stretched, like music played back at a lower tempo. Redshift becomes a kind of clock, because it tags an epoch in the universe's expansion. It tells us how much the universe has expanded since the light was emitted, and therefore how different the cosmic environment was. When we read Z, we are reading a ratio of scale factors, a compressed history written into a single number. Yet redshift is not a distance by itself, and the temptation to treat it as one must be resisted. To turn Z into a distance, you must assume an expansion history, which depends on cosmological parameters. Those parameters include the matter density, the dark energy content, and any spatial curvature, and each changes how the same redshift maps to kilometers or light years. This is where the documentary's mystery returns in a new costume, because the dependence is structural. The one-way story depends on how we define now, and cosmic distance depends on how we define the universe's time slices. We can describe the same observations with different coordinate choices, and the universe will not object, because the physics is in the invariance. Cosmology offers several legitimate distances, each tied to a different operational question that an observer might ask. The same object can have multiple distances at once without contradiction, because the definitions answer different questions. The language sounds abstract until you connect it to what telescopes actually measure. Comoving distance acts like an address in the expanding grid, a way to label positions in large-scale structure. It factors out expansion so that galaxy clustering can be compared across time, as if the cosmic web were drawn on a stretching fabric. In a graphic, comoving coordinates keep the grid fixed while galaxies drift with the expansion. Proper distance is the separation on a chosen cosmic time slice, and it answers a question we cannot observe directly. It tells how far the object is now, in that slicing, even though we never receive a now signal from it. Proper distance is a computed present, a present inferred from a past arrival. Luminosity distance is defined by how brightness falls off, because flux is what detectors count. It packages redshift dimming and time dilation into a number that preserves the inverse square form, which makes it practical. The photon energy is reduced by redshift, the arrival rate is slowed by time dilation, and both effects are folded into the definition. Angular diameter distance is defined by how size maps to angle, which is what images directly provide. It can behave non-intuitively at high redshift because geometry and expansion reshape light bundles over cosmic time. Distant objects can appear larger in angular terms beyond a certain redshift, a counterintuitive twist that reveals curvature and expansion together. These are not academic distinctions, because our instruments measure fluxes, angles, and spectra, not distance in isolation. Each observable naturally pairs with a different distance definition, and the definitions are built to keep equations usable. In practice, astronomers choose the distance that matches the measurement. then translate between them using a cosmological model. So when we say a galaxy is 10 billion light-years away, we must ask which distance we mean, even if the headline number sounds clean. We might mean look-back time in years, or a present-day proper distance in light-years. The phrase away hides the choice, and the choice matters more as redshift increases. The numbers can differ dramatically at high redshift, and the divergence is not a mistake. Expansion means the light travelled for billions of years, while the present separation grew beyond c times that travel time. The light did not break the speed limit, but the space between source and observer did not stay fixed either. That statement sounds like a violation until we remember the earlier chapters and the difference between local and global claims. Locally, nothing outruns light, yet globally the metric can expand, and proper distances can grow faster than c. The speed limit is about signals moving through space, not about the bookkeeping of distances defined on a chosen slice. The key is that c limits local signal propagation, not the rate at which a chosen distance measure changes under expansion. Causality still respects the light cone, even when the map stretches and the grid lines drift. The light cone is the universe's rulebook for influence, and the expansion does not erase its structure. This nuance builds tension, because it breaks the naive equation of distance with travel time that feels so natural. Light time is operational, but it is not the whole geometry, and cosmology forces us to hold both ideas at once. We can keep the travel time as the observable truth, while admitting that distance now is a model-dependent reconstruction. Now we can make the case against miles with more force, because the mismatch is conceptual, not merely numerical. Miles imply a static stage where distance is a single Euclidean fact, and the cosmos does not offer that stage. The universe offers a dynamic space-time where the meaning of simultaneous is not universal across vast separations. On Earth, a mile is tied to rods, surveys, and shared simultaneity, and those assumptions are quietly built into everyday measurement. Across galaxies, simultaneity is a convention, and the only shared structure is causal order. We can agree on which events can influence which, but we cannot demand a single global now without choosing a coordinate system. Light years keep the causal structure explicit, and that is their hidden power. They remind us that every measurement is a reception event here, tied to our clock and our past light cone. The unit itself whispers the method. You are counting the travel of information, not the reach of a physical ruler. They also keep the ladder honest, because the ladder is built from what arrives, not from what exists out there, in an absolute sense. Parallax is an angle measured now, Cepheids are brightness and period measured now, and supernovae are light curves measured now. The data are local, and the inferences are remote. In each case, we infer an emission event then, and we connect it to our reception event now through physics. The distance is a reconstruction, and the reconstruction is constrained by calibration, by astrophysical modelling, and by a chosen cosmological framework. When the framework changes, the interpretation shifts, even though the photons are unchanged. This is also where the earlier promise about constraints becomes clearer, because the universe is not infinitely permissive. Experiments can crush anisotropy in the two-way speed, and cosmology can cross-check models across many probes. If one rung disagrees with another, the tension is not ignored, it becomes a clue about dust, evolution, or the parameters themselves. But no observation hands us a universal present for a distant galaxy, and that absence is not a technical failure. The one-way ambiguity is not a loophole we forgot to close, it is the structure we must navigate. The universe gives us arrivals, and we build a coherent history by choosing a language that respects causality. Astronomy therefore treats the universe as a time machine, not because it is romantic, but because it is literal. Every deeper survey is a deeper slice into the past, and every longer exposure is a longer wait for older photons. In the visuals, the camera glides from bright nearby stars into faint reddish smudges, and the smudges are ancient. The mystery is that we build a coherent history from arrivals that never carry a present tense stamp. We infer the universe's timeline from delayed messengers and a chosen coordinate language, and we test that language against consistency. The result is a narrative anchored in measurement, yet haunted by the fact that now is a local privilege. Now the chapter tightens around a practical claim that sounds modest but changes how we think. Light years are not a poetic unit. They are the universe's native operational unit. They fit the way evidence travels, and they keep the observer's role visible in every number we quote. They compress the method into the number, which is why they feel so natural once you accept the premise. They say this is how long information took to reach us, and that travel time is what we can actually measure. Even when we later convert to kilometers, the light year keeps the causal story intact. Yet we must keep the final nuance in view, because it sets up the next chapter's stakes and prevents a seductive oversimplification. How far and how long ago are linked, but they are not identical, especially in an expanding universe. The link is real, but it is mediated by geometry, expansion history, and definition. Two objects with the same redshift can map to different distance measures if cosmological parameters differ, and that dependence is measurable. Change the matter density, dark energy, or curvature, and the conversion shifts, sometimes by billions of light-years at high Z. The photons carry the redshift, but the model determines how that redshift becomes a distance. That dependence is not weakness, it is leverage, because it turns distance measurements into tests of the universe's contents. By comparing supernova distances, baryon acoustic oscillations, and the CMB, we constrain the parameters that set the mapping. Agreement across these probes is not guaranteed, which is why it is so informative when it happens. Still, the mapping is a choice layered over data, and the choice must be stated plainly. We choose a cosmic slicing that makes the universe statistically simple. Then we compute distances within that language. The simplicity is not arbitrary, it reflects symmetries we observe, but it is still a coordinate commitment. The documentary's hook echoes again, now on the larger stage where our intuitions are most fragile. We can measure the round-trip constant with extreme precision, yet the one-way story depends on how we define now. In cosmology, that dependence is not a defect, because the universe is mapped by light, and light turns distance into time. Next, the story moves from measuring to limits, where light and expansion draw borders that no technology can negotiate. Horizons are not lines on a map, they are boundaries of what can ever be known. We will ask which regions can still send us new information, and which are already beyond causal reach. We will see how the light year becomes not just a ruler, but a warning. We teach that light speed is the universe's ultimate constant, yet no one measures its one-way speed without first choosing what counts as now. That single word, now, sounds innocent in conversation, but in physics it hides a rulebook. When two clocks are far apart, we do not merely read them, we decide how to relate their readings. The decision can be practical, mathematical, and internally consistent, yet it still shapes what we call a one-way travel time. This chapter interrogates the boundary between convention and physics, where light seems to slow, bend, or arrive late. We separate coordinate bookkeeping from observables, then we ask a sharper question that refuses to dissolve into language. Could vacuum itself hide a directional asymmetry that experiments would reveal as Lorentz violation? First, we narrow the claim we defend, because sloppy claims create fake paradoxes. Relativity does not say light always covers equal meters per second in every situation, in every coordinate grid, under every definition of distance. It says local physics in vacuum has an invariant speed c, measured in a local inertial frame where gravity and acceleration are negligible. That local clause matters more than it first appears, because nature rarely hands us perfect emptiness. The moment light enters matter, the story changes in ways we can measure directly with ordinary instruments. A material is not empty space, even when it looks like pure transparency under sunlight. It is a medium packed with charges, electrons bound to atoms, ions in lattices, sometimes free carriers in metals. When an electromagnetic wave passes, those charges respond, oscillate, and re-radiate fields that interfere with the original wave. What looks like a single beam is, microscopically, a continuous negotiation between field and matter. Refractive index is the simplest summary of that response, and it is already a clue that speed is not one thing. In many materials, the phase of a light wave moves at c divided by n, where n encodes the material's electromagnetic susceptibility. If you animate it, the crests slide forward like a marching pattern across a crowd. That phase speed can be less than c, and it can also exceed c, which sounds like trouble until we recall what a phase is. A phase is a repeating label on a sinusoid, not a carrier of surprises. If you paint stripes on a moving belt, the stripes can seem to race faster than the belt itself. Phase speed is not the speed of a message, and physics is strict about what counts as a message. It tracks how a crest advances, not how a pulse front carries new information. Relativity cares about causality, which is enforced by the fastest possible signal that can trigger a new event. Group velocity enters when we send a pulse with a bandwidth, rather than an infinite, perfectly monochromatic wave. The pulse has an envelope, and the envelope is what a detector usually registers as arrival. In ordinary transparent media, group velocity is also about c divided by n, so pulses arrive later than they would in vacuum. That delay is measurable with one clock at the receiver, and it needs no distance synchronization. You can place a photodiode at the far end of a fiber, start a timer locally when the pulse is launched, and stop it when the detector fires. The result is a practical 1n measurement of delay, even though it is not a one-way vacuum speed. Dispersion complicates the picture because n depends on frequency, and real pulses contain many frequencies. Different colours travel with different group delays, so pulses spread out, blur, and sometimes develop ringing tails. The medium becomes a filter as well as a slow corridor, reshaping what it transmits. In a vivid lab shot, a short pulse enters a glass block as a tight packet, then exits stretched and softened. The leading edge may remain sharp while the peak drifts, as if the pulse is being pulled apart. That visual is not metaphorical. It is the Fourier spectrum being delayed by different amounts. In some dispersive regimes, group velocity can exceed c, or even become negative, which is where headlines are born. The peak of a reshaped pulse can appear early, as if it outran light through the medium. Yet the resolution is that the peak is not the first new information, and the medium is not a passive track. The medium stores energy briefly in the motion of charges, then releases it with a phase delay that depends on frequency. What emerges is a reconstituted wave, not the same wave, simply moving slower. When the spectrum is sculpted, the location of the maximum can shift forward without any causal influence travelling superluminally. Information is tied to the front of a signal and to non-analytic features, the parts you cannot predict from a smooth continuation. Those features are constrained by the medium's causal response, encoded in Kramers, chronig relations that link dispersion to absorption. In plain terms, a material cannot delay some frequencies without paying a price elsewhere in its response. The front velocity stays at or below c in vacuum, preserving cause before effect even when peaks play tricks. If you modulate a carrier with a truly new bit, the earliest detectable change cannot arrive before the vacuum limit allows. The mathematics of analytic continuation is not philosophy. It is what keeps experiments from contradicting themselves. So slower than c in glass does not threaten relativity, and faster than c peaks do not rescue a loophole. It is light interacting with matter, storing energy briefly, then releasing it with a lag that depends on microscopic dynamics. The invariant claim is about local vacuum propagation and causal structure, not about every effective speed we can define. Plasmas add a second kind of slowdown that matters in space, and the visuals shift from lab optics to planetary skies. A plasma is a sea of free charges that can oscillate collectively, like a fluid that supports electrical waves. Its response is set by the plasma frequency, which depends on electron density. Below that plasma frequency, electromagnetic waves do not propagate, and above it they disperse in a distinctive way. The refractive index becomes frequency dependent even in a tenuous plasma, and the group velocity drops more at lower radio frequencies. That is why space is not an empty stage for signals, even when it looks black. Radio signals through the ionosphere arrive with frequency-dependent delays, and engineers treat this as a daily reality. A bright sunrise can change ionization, shifting the effective electron column overhead. The delay is not subtle when you care about nanoseconds, and modern navigation systems care intensely. Pulsars and fast radio bursts show this cleanly as a sweep in arrival times, a chirp painted across a time-frequency plot. High frequencies arrive first, then lower ones trail behind in a graceful curve. The delay maps electron density along the path, not a change in vacuum C. Even interplanetary space is not perfect vacuum for measurement, and the solar wind makes that obvious. The wind carries plasma outward, threaded by magnetic fields that vary with solar activity. In magnetized plasmas, different polarizations can split and rotate, producing Faraday rotation that astronomers measure as another diagnostic. The observable is time delay and dispersion, which can be modeled and subtracted, but only if you respect the physics. If you ignore the plasma, you might mistake a changing delay for a directional effect. The universe would seem to prefer one direction, when the real culprit is a changing medium. These media effects matter for our central question, because they mimic anisotropy if you are careless. A cable delay, a fiber delay, or an atmospheric delay can look like direction dependence when the environment is not symmetric. The one-way speed problem is already fragile, and media make it worse by adding hidden, drifting time offsets. Now we shift from materials to gravity, where the vacuum itself still enforces local C. General relativity says light follows null geodesics, and locally it always moves at c, even near massive bodies. Yet globally, travel time can stretch because spacetime is curved, and the geometry itself becomes part of the experiment. To picture this, imagine a beam skimming past a planet, traced as a thin line over a warped grid. The grid is not a physical fabric, but it is a useful visual for how distances and times are related. The photon does not feel a force in its own frame, it simply follows the straightest possible path available. Shapiro delay is the cleanest example of gravity adding time without changing local speed, and it has a concrete historical origin. In the 1960s, Erwin Shapiro proposed timing radar echoes that pass near the Sun, where space-time curvature is strong. The prediction was not that light slows like it does in glass, but that the coordinate travel time increases because the path runs through deeper gravitational potential. Radar signals sent past the Sun return later than flat geometry predicts, and the extra delay is measurable. The delay matches curved spacetime, not a slow photon, and it agrees with general relativity's quantitative form. It is one of those tests where the numbers are not merely suggestive, they are sharply constrained. This is not a one-way measurement either, and that is the point we keep returning to. Shapiro delay is extracted from round-trip timing, using one clock and a known ephemeris for planetary positions. It is a closed-loop observable that avoids distance synchronization, which is why it is so clean. Gravitational lensing shows the same principle in space rather than time, and the visuals become cinematic. Light rays bend around mass because the geometry guides null paths, and the sky turns into a hall of mirrors. Multiple images and arcs appear around galaxies and clusters, even though each photon locally moves at c. Time delays between lensed images add a second observable, and they are measured without needing two synchronized clocks. Different paths have different geometric lengths and different gravitational potentials, so their arrival times differ. The arrival time differences can be measured at one detector, then used to infer mass distributions and cosmological parameters. Here, the language of effective speed becomes dangerous, because coordinates can seduce us. In some coordinate choices, light's coordinate speed near a black hole can look reduced, as if the photon is wading through syrup. That reduction is a coordinate artifact, not a local physical slowdown, and it disappears in a freely falling frame. This distinction echoes our earlier chapters on simultaneity, where speed depends on how you slice spacetime into space and time. Coordinates can assign different one-way speeds, while preserving all local invariance and all measurable round-trip facts. Gravity makes that freedom more obvious, because there is no global inertial grid that covers curved spacetime without distortion. We now tighten the boundary between coordinate effects and measurable observables, because this boundary is the chapter's spine. Proper time along a world line is measurable by a clock carried along that path, and it is independent of coordinates. Round-trip light time is measurable by one clock and a mirror, even in curved spacetime with complicated geometry. One-way travel time between separated world lines requires a synchronization rule, and rules are choices. In curved spacetime, there is not even a unique natural synchronization across large regions, because there is no single notion of simultaneous everywhere. Any one-way speed you quote is entangled with your slicing, and slicing is a human-imposed structure. Rotation adds a twist that looks like anisotropy even in flat spacetime, and it is one of the most visually intuitive effects. The Sanak effect shows that light sent around a rotating loop returns at different times depending on direction. The difference is proportional to the loop area and rotation rate, and it survives even when the loop is in otherwise empty space. On a rotating platform, there is no global Einstein synchronization around the loop, and the failure is not a technicality. If you try to synchronize clocks all the way around, you come back with a mismatch, like a seam that will not close. The failure is geometric, tied to non-inertial motion, and it reveals itself as a measurable time difference. Ring laser gyroscopes measure Sagnac time differences as a beat frequency, turning geometry into sound like rhythm. Two counter-propagating beams resonate differently because the cavity is rotating, and their interference produces a slowly varying beat. The observable is local and closed loop, so it bypasses one-way timing, while still detecting rotation with extraordinary sensitivity. Earth itself is a rotating platform, so Sagnac is not a lab curiosity with polished mirrors. GPS must correct for it because signals travel in an Earth-centered rotating frame, where simultaneity cannot be globally consistent. Without correction, position errors accumulate quickly, and the system would drift out of usefulness within minutes. This matters for our theme because it creates an apparent directional asymmetry in travel times, and the asymmetry is real as a measured loop effect. Signals travelling eastward and westward in the rotating frame do not share the same coordinate travel time, yet it does not imply vacuum light speed differs by direction in an inertial frame, where the symmetry is restored. Sagnac also clarifies what breaks Einstein synchronization, and why the break is not a failure of relativity. In inertial frames, Einstein synchronization is globally consistent in flat spacetime, and you can extend it without contradiction. In rotating frames, simultaneity cannot be made single-valued around a loop, and the mismatch is the measurable residue. So far, every apparent deviation from simple C has a clear cause, and the causes are physical, not mystical. Media introduce dispersion and delays through interaction, storing and releasing energy in microscopic degrees of freedom. Gravity changes geometry and coordinate descriptions while preserving local C, and rotation breaks global simultaneity and creates loop asymmetries. Now we ask the harder question promised earlier, the one that does not evaporate into definitions. Could there be a true anisotropy in vacuum itself, not removable by coordinates, not explainable by media or gravity? If so, it would show up as Lorentz invariance violation in observables, the kind that no synchronization convention can hide. Lorentz invariance is not just a philosophical preference, and it is not merely a historical artifact of Einstein's era. It is the symmetry that makes the laws of physics look the same in all inertial frames, and it threads through electromagnetism, quantum field theory, and particle kinematics. It is tested by comparing clocks, resonators, particles, and photons as Earth moves and rotates through space. There is also a historical arc behind these tests, stretching back to the late 19th century. The Michelson-Morley experiment was designed to detect motion through an ether by looking for a change in interference fringes. Its null result did not end curiosity, it redirected it towards symmetry, and later generations refined the question with better tools. Modern tests often use resonant cavities because they turn speed into frequency, and frequency is what laboratories measure best. A cavity supports standing waves whose resonance depends on the effective optical path length. If light's propagation depended on direction, a cavity's resonance would shift as the apparatus rotates, and the signal would be a periodic modulation tied to sidereal time. Michelson. Morley descendants now use cryogenic optical resonators and microwave cavities, where thermal noise and mechanical drift are suppressed. They compare frequencies with exquisite stability over long runs, watching for tiny periodic patterns as Earth turns. The absence of modulation constrains anisotropy in the two-way speed to extreme levels, far beyond what intuition can picture. Kennedy, Thorndike-style tests add sensitivity to boost dependence, which is a different way Lorentz symmetry could fail. They compare cavities with different geometries while Earth's velocity changes through the year as it orbits the Sun. Any change in C with speed relative to a preferred frame would leak into frequency ratios, producing an annual signature. Atomic clock comparisons test Lorentz symmetry in matter, as well as light, and they do it with quantum precision. Different atomic transitions respond differently to hypothetical symmetry-breaking terms, because their energies depend on angular momentum and internal fields. As Earth rotates, the orientation of quantization axes changes relative to the sky, and any preferred direction would reveal itself as a rhythmic drift. These experiments do not directly measure one-way light speed, and that limitation is part of their strength. They constrain the structure of spacetime symmetries that would make one-way anisotropy physically meaningful. They attack the loophole by looking for effects no synchronization convention can hide, because the predicted signals are in closed systems and invariant comparisons. The standard model extension provides a framework for that search, and it brings order to what could otherwise be an ad hoc catalogue. It parameterizes all possible small Lorentz violating terms consistent with known fields and basic principles like energy conservation. Each coefficient predicts specific signatures in photons, electrons, nucleons, and gravity, which lets experiments report constraints in a common language. In the photon sector, SME terms can cause direction-dependent phase velocities or vacuum birefringence, both of which are testable. Birefringence would rotate polarization or split modes over long distances, turning empty space into a weak crystal. The sky becomes a laboratory with baselines no Earth experiment can match, because the light has travelled for millions or billions of years. Astrophysical constraints are brutal because light travels for so long that tiny effects can accumulate into visible damage. Polarization from distant galaxies and gamma-ray bursts arrives with coherence that survived intergalactic space. If vacuum birefringence were present at appreciable levels, polarization would wash out, and the sky would look more randomized than it does. Time-of-flight tests use sharp transients like gamma-ray bursts and pulsars, where timing is part of the signal's identity. If high-energy photons travelled at slightly different speeds, arrival times would correlate with energy in a systematic way. Observations place tight bounds, though source physics must be modelled carefully, because the emitter can also create energy-dependent delays. Some searches look for anisotropy tied to a preferred cosmic frame, and the idea has a natural reference. The cosmic microwave background defines a practical rest frame for large-scale matter, and we can measure our motion relative to it. A true preferred frame could imprint orientation-dependent effects as Earth rotates relative to that frame, producing sidereal patterns in precision data. Yet even here, we must keep the conceptual line clear, because cosmology can mislead the unwary. A cosmological rest frame does not automatically violate local Lorentz invariance, and it is not the same as an ether. It is a property of the universe's matter distribution, not a modification of a local vacuum laws, and local experiments can still respect Lorentz symmetry perfectly. The stakes rise because the one-way speed ambiguity could tempt us into thinking anything goes, as if definitions can rewrite reality. Reichenbach's epsilon freedom lets us repetition one-way times while keeping round-trip c fixed, and that is a coordinate freedom inside special relativity. It is a reminder that some quantities are not observables until we add a convention. A true vacuum anisotropy would be different, and it would refuse to stay hidden in language. It would change closed-loop observables, resonance conditions, polarization transport, or particle kinematics in ways that survive any relabeling. It would not be erasable by redefining simultaneity, because it would alter invariance that experiments can compare without distant clock agreements. So we separate two questions that sound similar but are not, and the separation is the chapter's key discipline. One is whether one-way speed in an inertial frame is directly measurable without convention, which is a question about operational definitions. The other is whether physics contains a preferred direction that changes measurable outcomes, which is an empirical question about symmetry. The first remains a matter of definition because it depends on distant clock synchronization, and synchronization is a choice. The second is an empirical question, and nature answers it through Lorentz tests that look for periodic drifts and orientation signatures. The answer so far is that any violation is extremely small enough that it has not disrupted any precision technology built upon relativity. Gravity complicates Lorentz tests in subtle ways, and that must be stated to keep the story honest. In curved space-time, local Lorentz symmetry still holds in general relativity, and freely falling labs recover special relativity in small regions. But global comparisons across Earth's gravitational potential require careful modelling of redshift and time dilation, because clocks at different heights do not tick at the same rate. GPS again becomes a case study in separating coordinate choices from observables, and it is a case study we live inside. Satellite clocks tick faster than ground clocks due to gravitational redshift, because they sit higher in Earth's potential well. They also tick differently due to special relativistic time dilation from orbital speed, and both effects are large enough to ruin navigation if ignored. The system works because it models both effects and defines a coordinate time for navigation, a shared bookkeeping variable. That coordinate time is a convention chosen for engineering, not a universal cosmic now, and it is implemented through control segments and clock steering. Yet the corrections are physical and measurable as clock rate differences, and their necessity is a daily validation of relativity. SANAC corrections in GPS show how rotation creates apparent one-way asymmetries, even when the underlying local physics is symmetric. Signal travel times differ eastward and westward in the rotating Earth frame, and the difference depends on geometry and Earth's angular velocity. The correction is computed from that rotation, then validated by system performance, which is the most unforgiving kind of test. This is the documentary's boundary line in practice, and it is where philosophy meets engineering. We can choose a synchronization convention within an inertial frame and keep one-way speed conventional because the convention is consistent. But when we move to rotating frames, the convention cannot be global, and loop effects become unavoidable observables that show up in real data. Media delays, gravitational delays, and rotation effects all teach the same discipline, and they teach it with different accents. When light arrives late, ask what physical interaction or geometry produced the delay, and whether it is frequency dependent. Then ask whether the claim depends on coordinates or on closed-loop measurements, because closed loops are where conventions lose their power. Now we return to the central question with more precision and with fewer places to hide. If one-way speed is conventional in inertial frames, can the universe still hide an anisotropy? Only if that anisotropy changes invariance that experiments can detect, and only if it survives the many cross-checks built into modern precision physics. The best constraints come from combining many kinds of tests, because different experiments are sensitive to different kinds of symmetry breaking. Resonators probe direction dependence in controlled labs, where temperature and vibration are tamed. Atomic clocks probe boost and orientation dependence in matter, where quantum transitions serve as stable rulers. Astrophysics probes cumulative effects over cosmic distances, where the universe supplies the baseline. The combined picture is not that we have proven absolute isotropy by definition, as if a choice of words could settle it. It is that any real anisotropy in vacuum would have left fingerprints in frequencies, polarizations, and arrival times across many platforms. Those fingerprints are not seen within very tight bounds, and the absence is itself a powerful observation. So the mystery survives in a narrower form, and the narrowing is what makes it interesting. The one-way speed in vacuum remains tied to how we define distant simultaneity in inertial frames, which is a language choice that preserves all round-trip facts. It is a reminder that some questions are about how we coordinate our descriptions, not about what photons really do between clocks. But the universe does not give us unlimited freedom to rewrite physics, and that is the other half of the tension. If we tried to encode a real directional asymmetry into coordinates, experiments would still detect it, through Lorentz-violating observables that no convention can erase. The constraints are so strong that any hidden anisotropy must be vanishingly small, or it must mimic symmetry with extraordinary precision. This chapter's conclusion is careful because it must hold two truths at once, without letting either collapse the other. One-way speed in vacuum is not directly measurable without a convention about now, and that is a structural fact about space-time descriptions. Yet nature tightly constrains any true anisotropy that would rise above convention, because it would alter closed-loop observables and symmetry tests. That tension is not a loophole. It is the shape of modern measurement, where definitions and experiments share the stage. We measure round-trip C with extreme precision, then build maps using a chosen simultaneity language that keeps the accounting consistent. In cosmology, light turns distance into time, making the light year our most honest ruler, and also our most haunting one. Next, the story moves from these local and near-Earth constraints to cosmic limits. We will ask how horizons turn light speed into boundaries of knowledge, not just a number. We will see where measurement ends, even in principle, and where convention becomes the only remaining map. We teach light as the ultimate constant, yet its one-way speed hides behind synchronized clocks and agreed definitions. GPS is where that mystery stops being abstract and becomes a daily utility, because every location fix is a claim about when a signal left a satellite. Every distance estimate is a time difference multiplied by an agreed value of c, an agreement so routine we rarely notice it. Start with the basic promise and picture the scene as it really looks. A receiver on Earth sits under an invisible web of radio transmissions, listening for coded signals from multiple satellites that sweep across the sky. Each satellite broadcasts a timestamp and its own orbital data, wrapped into a navigation message that repeats with disciplined regularity. The receiver compares the received code phase to an internal replica, and from that comparison, it estimates how long the signal travelled. That comparison is not a single ping in the way a sonar pulse feels intuitive. It is a correlation process, sliding a locally generated code against the incoming code until the peaks line up. When the alignment locks, the receiver has a measurement of apparent delay, and it tags that delay with its own imperfect clock reading. In plain terms, it is matching patterns, then converting the match into a time of flight. The receiver does not measure a geometric range at first, even though the final answer looks like a distance. It measures a pseudo-range, a range corrupted by clock offset and other delays that the receiver must model or estimate. The receiver clock is not an atomic clock, so its time is unknown and drifts with temperature and electronics. That unknown becomes an extra variable solved alongside position, turning navigation into a joint problem of geometry and timing. 4 satellites are the minimum for a full solution, and the reason is purely algebraic and deeply physical at once. 3 unknowns describe receiver position in space, usually expressed in Earth-centered coordinates. A 4th unknown describes receiver clock bias relative to GPS time, which acts like a hidden shift applied to every measurement. With 4 pseudo-ranges, the receiver solves 4 equations at once, and the solution is the only place the spheres can meet. This is trilateration, but it is not the clean sphere intersection taught in cartoons, where 3 perfect spheres neatly cross at a point. Each pseudo-range defines a sphere centered on a satellite position at transmit time, but the radius is contaminated by the receiver's clock error. The spheres do not meet until the receiver adjusts its own clock, and that adjustment is not optional. The fix is a simultaneous solution for where and when, because where is encoded in when. Even this when is already loaded with convention, and GPS makes that unavoidable in a way textbooks often soften. The satellite timestamp is not a direct reading of a universal now, floating above the world like an absolute metronome. It is a coordinate time label inside a defined reference system, maintained by institutions and hardware rather than metaphysics. GPS works because everyone agrees to use that label consistently, and because the system is engineered to keep the agreement stable. Now the system's hidden dependence on relativity becomes unavoidable, and the numbers are too large to dismiss as philosophical decoration. Satellite clocks do not tick at the same rate as clocks on Earth's surface, even if they were built in the same factory. They move fast in orbit, so special relativity predicts time dilation that reduces their accumulated proper time. They sit higher in Earth's gravitational potential, so general relativity predicts gravitational redshift that makes them tick faster than clocks deeper down. The special relativistic piece is straightforward in sign, and it follows from the geometry of space-time rather than any mechanical slowing. A moving clock accumulates less proper time than a stationary one, relative to an Earth-centered inertial frame used for modelling. GPS satellites orbit at about 3.9 kilometers per second, fast enough that the effect is measurable every day. That speed makes their onboard clocks run slow by roughly 7 microseconds per day, even before we consider gravity. The gravitational piece flips the direction, and it is often the part that surprises people who learned gravity as a force. Higher altitude means weaker gravity and faster ticking relative to clocks deeper in the potential well, because space-time curvature changes the rate at which proper time accumulates. GPS satellites orbit around 22,100 kilometers above Earth, well beyond most of the atmosphere and far above the geoid. That altitude makes their clocks run fast by about 45 microseconds per day, dominating the special relativistic slowdown. The net effect is not subtle for navigation, and the system would visibly unravel without compensation. Add the 2 contributions and the satellite clocks run faster by about 38 microseconds per day relative to clocks on Earth's surface. Multiply that time error by c, and the implied range error is about 11 kilometers per day, a drift so large that a car would appear to jump across a city. Without correction, GPS would fail quickly and visibly, not as a gentle degradation but as a daily catastrophe. So GPS bakes relativity into its design, not as a patch, but as a starting assumption. Satellite oscillators are preset with a frequency offset on the ground, so that once in orbit their ticking rate matches the intended GPS coordinate time. The adjustment is tiny in fractional terms, but relentless in its consequences, because it accumulates every second. The system also applies ongoing clock steering and uploads corrections, because real clocks and real orbits never behave perfectly. This is where the documentary's central question returns with teeth. We cannot measure one-way light speed without synchronized clocks because one-way time already assumes a shared definition of simultaneity. GPS appears to do it constantly, yet it succeeds by defining synchronization first, then building everything else on top. The system does not discover simultaneity, it imposes it, quietly, operationally, and with astonishing discipline. To see the imposition, separate the clocks from the geometry and watch what remains. GPS time is a timescale maintained by a network of atomic clocks, distributed across control stations and monitored with careful statistical filtering. It is realized by the control segment and disseminated by satellites, which act as broadcasters rather than ultimate authorities. It is close to UTC but not identical, because leap seconds are handled differently, and because GPS prioritizes continuity over civil time adjustments. GPS time is not the proper time of any single clock, and that detail matters more than it seems. It is a coordinate time for an Earth-centered reference system, designed so that equations stay stable across the globe. It is a bookkeeping variable that makes the navigation solution tractable, even when different observers move and sit at different gravitational potentials. It is chosen to be practical, not metaphysically privileged, and practicality is the point. The receiver's job is to align itself to that coordinate time, even though it has no direct access to the master clocks. It does this by solving for its clock bias, which becomes part of the position solution rather than an afterthought. That bias is not a nuisance term, it is the bridge between local proper time and the system's shared time. The bridge is what makes one-way signaling operational, because it turns a local reading into a network-compatible time label. Yet the bridge still rests on measurable two-way foundations, and GPS engineers never forget that. The control segment monitors satellites with ground stations spread across the planet, watching their signals rise and set like artificial stars. It uses tracking data, round-trip ranging, and network consistency checks that compare many paths at once. Those closed-loop measurements keep the timescale coherent and detect drifts, because a drifting satellite clock is not a small error, it is a moving target. This is the engineering version of the earlier chapter's claim translated into hardware and procedures. Two-way measurements anchor the system, because they avoid distant synchronization ambiguity and expose inconsistencies that one-way stories can hide. One-way use becomes possible only after the network defines a convention and enforces it, day after day, upload after upload. GPS is a convention stabilized by feedback, and the feedback is what makes it feel like fact. Now introduce the frame issue that quietly breaks naive timing, even if every clock were perfect. Earth rotates, and the receiver is on a rotating platform carried eastward by the planet's spin. Satellite orbits are best described in an Earth-centered inertial frame, where Newtonian-like orbital motion is clean and symmetric. But users want coordinates fixed to Earth's surface, an Earth-fixed rotating frame that matches maps, roads, and coastlines. Those frames do not share a single global simultaneity, and rotation is the reason the trouble cannot be smoothed away. In a rotating frame, Einstein's synchronization cannot be extended consistently around Earth without producing a mismatch when you return to your starting point. The mismatch shows up as the Sanat effect, first observed in rotating interferometers long before GPS existed. Signals traveling with or against rotation have different travel times in Earth-fixed coordinates, even though the physics in an inertial frame remain symmetric. The Sanat correction is not optional, and its magnitude is large enough to matter in ordinary navigation. If you ignore it, eastward and westward paths accumulate timing errors that do not cancel out in the position solution. The error depends on Earth's angular velocity and the area swept by the signal path, which makes it geometry dependent rather than constant. For GPS, it can reach hundreds of nanoseconds, which means tens of meters, an error you can see on a street corner. State the correction in the simplest operational way, because the implementation is as revealing as the concept. Convert satellite and receiver positions into an Earth-centered inertial frame for signal propagation, where C is isotropic by convention, and the equations are simplest. Compute the light time in that inertial frame, then transform back to Earth-fixed coordinates and add the Sanat term. The correction looks like a technical footnote, yet it is a direct consequence of how simultaneity behaves on a rotating world. This step is a reminder that speed depends on the coordinate grid, even when the underlying physics respects relativity. In the rotating Earth-fixed frame, the coordinate speed of light becomes direction-dependent, because the coordinates themselves twist through space-time. In the inertial frame, it is symmetric under Einstein synchronization, which is why the system prefers it for propagation calculations. GPS chooses the inertial frame as the clean propagation stage, then translates the result back into the rotating language people use. The choice is not arbitrary, because it is testable by performance, and performance is the ultimate judge in navigation. If the SANAC term is wrong, the solution residuals grow, and the receiver cannot reconcile its measurements across satellites. If the relativistic rates are wrong, clock corrections drift predictably, and the control segment sees the pattern immediately. The system's success is a continuous experiment that punishes bad conventions, which is why the conventions are chosen with such care. Now add the smaller corrections that still matter at nanosecond levels, because GPS lives in a regime where small becomes operational. Satellite orbits are not perfect circles, so speed and gravitational potential vary over each orbit. That variation produces periodic relativistic effects on the clock rate, a rhythmic speeding and slowing that rides on top of the daily offset. GPS models this with an eccentricity correction term, because even a tiny periodic timing error becomes a repeating position error. Signal propagation is also not vacuum propagation, and the atmosphere becomes part of the instrument. The ionosphere introduces a frequency-dependent group delay, because free electrons change the effective refractive index for radio waves. The troposphere introduces a mostly frequency-independent delay tied to pressure and water vapor, and it varies with weather and elevation angle. Receivers estimate or model these delays, and dual frequency measurements can remove much of the ionospheric term by comparing how two frequencies are delayed differently. Multipath adds another layer of timing ambiguity, and it is the urban signature of GPS. Reflections from buildings, vehicles, and terrain create delayed copies of the signal that arrive a fraction of a microsecond later. The receiver's correlator can be pulled off the true line of sight arrival, because it is trying to lock onto a distorted composite. Modern receivers use antenna design, narrow correlators, and signal processing to reduce this error, but the city always fights back. All these effects reinforce the same theme, and the theme is almost philosophical even when it is expressed in code. The observable is a received code phase and a local clock reading, both of which are immediate and local. The inferred quantity is a transmit time in a shared coordinate system, which is distant and model dependent. Distance emerges from a model that connects those two events, and the model carries assumptions about frames, synchronization, and propagation. This is the earthbound mirror of cosmology's method, and the parallel is more than poetic. In astronomy, we receive photons and infra-emission times, often from objects we can never visit or synchronize with. In GPS, we receive radio codes and infra-transmit times from satellites that are physically reachable but temporally defined by convention. In both cases, the map is built from arrivals, not from direct access to distant presence, and that limitation shapes what we can claim. Now confront the one-way question directly inside GPS, because it is the heart of the chapter's mystery. Does GPS measure one-way light speed from satellite to receiver, as if it were simply reading a stopwatch on the sky? It measures a one-way travel time relative to GPS time, and that distinction matters. GPS time is defined through a synchronization convention implemented by the network, then enforced by monitoring and correction. If we change the convention, we could reshuffle one-way times while preserving round-trip consistency, and the mathematics would still close. The receiver would still get a position, but the coordinate labels would shift, and the interpretation of when would move with them. The physical predictions that matter are invariant residuals and closed-loop checks, because those are what the system can actually test. The one-way narrative is a language layered on those invariants, and the language is chosen for clarity. This is where Reichenbach's epsilon freedom becomes concrete, not as an abstract parameter, but as an engineering possibility. You can choose different splits of A to B and B to A times and keep the round trip constant, because the observable is the closed loop. GPS effectively chooses the Einstein split in an inertial frame, because it makes the equations simplest and the network easiest to maintain. The system selects convenience, then enforces it with calibration, which turns a choice into a stable standard. Yet the selection is constrained by the need to be globally consistent, because GPS is not one experiment but a planet-wide coordination problem. A bad convention would break the network's ability to maintain a single timescale, and it would amplify errors when transforming between inertial and rotating frames. It would also complicate orbit determination and clock prediction, which are already delicate tasks. GPS shows that conventions are free in principle but costly in practice, and cost is what disciplines freedom. The deeper point is that GPS turns time into distance by definition, and that definition is already embedded in modern metrology. A meter is defined by how far light travels in a fraction of a second. Using c as an exact number, rather than a measured one. GPS extends that definition into a planetary coordinate system, distributing it through signals and algorithms. It makes a global ruler out of synchronized timestamps, and it does so with a precision that would have seemed impossible a century ago. So when your phone reports a distance, it is reporting a time comparison, dressed in the familiar units of space. The receiver is solving for the intersection of light cones in a chosen coordinate grid, even if the interface shows only a blue dot. Each pseudo-range is a statement about a null path from satellite to receiver, constrained by the speed of light in the model. Position is the event where those null paths meet, and time is the hidden coordinate that lets them intersect. This is why relativity is not an exotic correction added at the end, like a footnote to Newtonian intuition. Relativity is the core that makes the timing model coherent across speeds, heights, and rotation, because those are exactly the conditions satellites inhabit. Without time dilation and gravitational redshift, the clock network would not stay aligned for even a day. Without SANAC, the rotating Earth grid would not match inertial propagation, and the map would tear along east-west lines. Now tighten the mystery again, because GPS seems to contradict the opening hook in a way that feels almost provocative. We said no one measures one-way light speed without assumptions, because synchronization is the hidden prerequisite. GPS appears to do it billions of times per day, in every car, ship, and phone. The resolution is that GPS measures one-way travel time within an agreed synchronization framework, and the agreement is the real instrument. That framework is not flimsy, because it is anchored by two-way calibration and constant monitoring that expose drift and inconsistency. It is not arbitrary, because it is chosen to match the symmetries of relativity and the practical needs of global coverage. It is not invisible, because its failure would show up as immediate navigation error, and users would notice within minutes. GPS makes the convention operational, and therefore trustworthy, even though it remains a convention. But it still remains a convention, and that matters for how we talk about space and time in everyday language. GPS does not reveal a universal present shared by satellite and receiver, because relativity does not offer that gift. It provides a coordinate present that lets engineering work, a shared slice of time that is defined rather than discovered. It is negotiated now, maintained by a disciplined network, and the discipline is what makes the negotiation feel natural. This is the climax of the documentary's argument at human scale, because it shows how deep physics becomes ordinary without losing its strangeness. We live inside a relativistic coordinate system and call it common sense, because the interface hides the assumptions. We navigate by defining simultaneity, then treating that definition as if it were simply how the world is. The mystery is not that the system works, it is that it works so well, and that we rarely ask what "so well" is built from. Now pivot outward, because the same logic scales to the sky, and the transition is almost seamless. If timekeeping conventions can build a global navigation system, they can also build a cosmic map, where the signals are older and the distances are larger. Cosmology also chooses a time coordinate, then translates light arrivals into distances, using models that must be consistent across the observable universe. The light year is not poetry, it is the same operational move, extended until the numbers become awe. In GPS, we pick an Earth-centered inertial frame and a coordinate time, then we turn arrivals into positions. In cosmology, we pick a cosmic rest frame and a cosmic time slicing, then we turn arrivals into histories. In both cases, the choice is guided by observed symmetries and by the demand for consistency, because inconsistency shows up as residuals and contradictions. In both cases, the map is a model that turns light travel into structure, and the structure is only as good as the timekeeping behind it. This returns us to the central question with maximum clarity, and it invites a final, unsettling observation. The round-trip constant is a measured fact, and the one-way story is a chosen language that rides on synchronization. GPS proves that the language can be powerful enough to steer airplanes and guide ambulances, even through storms and city canyons. It also proves that the language is maintained, not discovered, because maintenance is what keeps the now coherent. Next, the story moves from Earth's navigation grid to the universe's ultimate limits. We will ask where light and expansion draw horizons that no synchronization convention can cross. We will see how the same light that maps the cosmos also fences it in. We began with a hook that still sounds like a trick, especially when you see it written on a lab wall. Light is our ultimate constant, yet its one-way speed stays unmeasured. Now we resolve the puzzle without dissolving it into wordplay, because the issue survives every clever rephrasing. The answer is precise, and it is also philosophical. 1 part metrology, 1 part geometry, and 1 part language. A one-way speed needs a one-way time, not a round-trip average disguised as a straight line. One-way time needs 2 distant clocks that already agree even before the measurement begins. To make them agree, we must define distant simultaneity, meaning what it takes for 2 separated events to count as happening at the same time. Any definition uses signals or transport, and both import assumptions that cannot be eliminated by better hardware. Picture 2 clocks on separate benches, labelled A and B, in a long corridor of a quiet laboratory. Between them is open space, cables, air currents, and a subtle fact. Time is not a universal sheet laid flat across distance. If we synchronize by light signals, we must assume a split between outbound and inbound travel times, because only the round trip is directly timed at one location. That split is the convention, and it is where the apparent loophole lives. Einstein's synchronization chooses the simplest split, and it is simple in a very specific way. It sets the one-way times equal, so the one-way speed becomes c by definition within that coordinate choice. This is not a cheat so much as a rule of grammar for spacetime, like agreeing on what a word means before debating a sentence. Once you adopt the rule, you can speak consistently, and your predictions become testable. Reichenbach's epsilon shows the freedom more explicitly, and it does it with a parameter that slides between possibilities. Different splits change one-way speeds while preserving every round-trip result, so the closed-loop observables stay fixed. In that picture, epsilon is not a new force or a hidden medium, and it does not add extra physics by itself. It is a reminder that simultaneous is partly a coordinate choice, even in empty space. This is why the one-way speed cannot be directly extracted from experiments that only compare local readings, no matter how refined the electronics become. The circle is structural because any attempt to compare separated times already presumes a method of comparison. You can carry a clock from A to B, but then you must assume something about how motion and acceleration affect it. You can send a signal, but then you must assume something about how long it takes to go. Historically, this problem did not appear as a mere classroom paradox, because it grew out of real tension in 19th century physics. Maxwell's equations predicted electromagnetic waves with speed c, and experiments like Michelson. Morley failed to reveal motion through an ether. The failure was not just negative data, it was a demand for a new framework, because the old one needed a preferred rest frame. Einstein's 1905 move was to treat the constancy of light speed as a principle, then accept the consequences for simultaneity. Yet the story is not that c is arbitrary, and it never was, even when the one-way question is left open. The robust measurement is the round-trip speed, and it is measured relentlessly, in ways that pile up from tabletop optics to space missions. Interferometers, cavities, and timing loops all close the path, so the measurement becomes a comparison at one place. One clock and a return signal turn travel time into an observable, and the observable is stubbornly stable. In a Michelson interferometer, for example, light splits, traverses 2 perpendicular arms, and recombines to form fringes that shift with phase. The phase depends on round-trip travel, so the apparatus is naturally blind to one-way assignments. Optical cavities refine the idea by trapping light between mirrors, letting it bounce thousands or millions of times. The resonant frequency depends on the cavity length and the round-trip speed, so tiny drifts become measurable as beat notes. Modern metrology goes further and locks the definition itself, turning the constant into a standard rather than a target. The meter is defined so c is exact, and time sets length through the second, which is anchored to atomic transitions. When you hear that c is exact, it does not mean we stopped caring about measurement, and it does not mean nature is being forced to comply. It means we chose to define our ruler in terms of a clock, because clocks became the most reproducible instruments we have. So what is physical if the one-way story depends on a convention, and the convention sounds like a choice? The physical content lives in invariance and constraints, things that every admissible coordinate language must agree on. First, local measurements in vacuum always yield c, and local matters in a technical sense. In any sufficiently small inertial lab, light speed is the same in every direction, once you use standard rods and standard clocks. That local statement is not a slogan, It is an operational claim about what happens when you build the experiment inside a region small enough to ignore curvature and tidal effects. In that limit, special relativity becomes the rulebook, and the rulebook keeps winning. Second, causal structure is invariant, and it is visible in the geometry of light cones. Light cones carve spacetime into what can influence what, independent of coordinates, because they are defined by the null paths that light can actually take. That structure is not bookkeeping, and it is not a mere diagram in a textbook. It is the operational rule that no local signal outruns light, and cause precedes effect for time-like separated events. If you imagine a flashbulb going off, the future light cone is the expanding sphere of possibility, sweeping outward at sea. Every event inside that cone can be reached by something travelling at or below light speed, while events outside remain causally disconnected for now. Third, Lorentz symmetry is tested to extreme precision, and the tests are diverse enough to resist a single loophole. Resonators, clocks, particles, and astrophysical polarization agree, even when the experiments are rotated, boosted, cooled, or carried into orbit. Some tests compare atomic clock frequencies as Earth turns, looking for direction-dependent shifts that would betray a preferred frame. Others examine high-energy particles whose lifetimes and dynamics would change if spacetime treated directions unequally. Those tests do not hand us a convention-free one-way speed, and they do not pretend to. They do something deeper and harder to evade, because they constrain the structure that any convention must respect. They constrain any real anisotropy that would change closed-loop observables, which is where physical effects cannot hide. If vacuum preferred a direction, it would leave fingerprints in resonant frequencies, interference patterns, and the propagation of polarized light. So the freedom we keep is narrow, and it is a freedom of labeling rather than a freedom of outcomes. We can relabel simultaneity in inertial frames, but we cannot rewrite causal order, and we cannot change what returns to the detector. This is the core synthesis, and it is worth lingering on because it feels like a paradox until it clicks. One-way speed is tied to how we define now across distance, while C anchors spacetime's geometry as the conversion between temporal and spatial intervals. In other words, the ambiguity is not about whether light really moves, or whether the universe is hiding a secret directional speed. The ambiguity is about what it means to compare distant times without already having a comparison rule. Now we shift from the lab's clocks to the universe's map. The same logic scales up and the stakes become cosmic because the sky is not a laboratory bench we can walk across. Cosmology does not observe distance directly, at least not in the way you measure a room with a tape. It observes light received here, with arrival time, direction, spectrum, and brightness, and then it infers what must have happened far away. The primary observable is not miles, and it is not even distance in the everyday sense. It is light that has already travelled, carrying information from an earlier state, and arriving with its wavelength stretched by the universe's expansion. Every galaxy is seen on our past light cone, and that phrase is not poetic, it is literal geometry. The sky is not a snapshot of now, because there is no shared cosmic now that all distant places can agree on. When we say a galaxy is a billion light-years away, we're also saying we see it a billion years ago, modulo the details of expansion history. That is the honest meaning, and it changes how you picture the universe in your mind. Even when we convert to kilometers, the inference still begins as time, because the raw data are photon arrivals. Distance is reconstructed from light time plus a model, and the model specifies how space-time stretches between emission and detection. Redshift is the key clock in that reconstruction, and it is measured directly from spectra as shifted absorption and emission lines. It encodes how much the scale factor has grown during the photon's journey, turning wavelength into a record of expansion. At low redshift, Hubble's law links redshift to recession and to distance approximately, and the approximation is good because the universe has not changed much over the travel time. At higher redshift, the link becomes model dependent because the expansion rate evolves. To turn redshift into distance, we need an expansion history, which is a function rather than a single number. That history is inferred from many probes that cross-check each other, because no single method is trusted alone. Standard candles like Type Ia supernovae tie brightness to distance through calibration, and the calibration itself is a chain of careful comparisons. The idea is simple: dimmer means farther, but the execution demands corrections for dust, colour, and intrinsic scatter. Standard rulers like baryon acoustic oscillations tie angles to co-moving scales, using a pattern imprinted by sound waves in the early plasma. The ruler is not a physical stick, it is a statistical feature in the galaxy distribution, yet it behaves like a known length. The cosmic microwave background anchors the early universe, and fixes a reference epoch. Visible is a nearly uniform glow with tiny temperature ripples. Those ripples encode the physics of the primordial plasma, and they set a scale that later structure must respect. Together, these datasets constrain the parameters that define the distance scale, and they do it by forcing the story to be consistent. If one probe demanded an expansion history that broke another probe, the mismatch would not stay hidden. Notice what never appears in the raw data. No matter how advanced the telescope becomes, we never receive a tag that says what time it is over there right now, because the photons cannot carry a simultaneity certificate. We receive photons and interpret them, and interpretation is not a weakness, it is the method. We infer emission time in a chosen cosmic slicing, then infer distance in a chosen metric, and then we test whether the inferred picture coheres. That slicing is not arbitrary, but it is still a choice, and the choice is guided by symmetry and by what the sky actually looks like. We use the FLRW symmetry because the universe looks homogeneous and isotropic on large scales, once local clumps are averaged out. Within that framework, cosmic time is the proper time of co-moving observers, meaning observers who ride with the average expansion and see the universe as isotropic. It is a convention guided by symmetry and by simplicity, and it becomes a shared reference because it works. It is also constrained by consistency, which is where physics pushes back against mere preference. If the slicing were wrong, the ladder would not close and the residuals would not behave, and the disagreements would show up as patterns rather than noise. This is where the one-way speed theme returns in a new form, and it returns almost unnoticed. Cosmology is built from one-way arrivals without synchronized distant clocks, because the universe does not offer us a return channel. We cannot send a ping to a remote galaxy and wait for an echo, not even in principle on human timescales. We can only receive, compare, and model, and then ask whether the model predicts the next observation. So cosmology naturally speaks in light time, and the language is honest about the causal setup. Light years and look-back time are not a workaround for ignorance. They match the fact that information travels at finite speed. If you watch a deep field image assemble on a screen, pixel by pixel, you're seeing a time stack. Nearby galaxies appear as mature spirals, while distant ones look smaller, bluer, and more irregular, history arranged by distance. Now reframe the old argument about units. Miles are fine, but they hide what is operationally primary, which is the timing of signals and the modelling of their journey. A mile is a length you could imagine laying down, step by step, in a shared present, as if the whole route exists in the same now. The cosmos does not grant that present, because simultaneity across vast distance is not given. A light year encodes the method, and it encodes it in a single phrase. It says distance is inferred from light travel, and from the finite speed that limits knowledge, even when we later translate the result into meters. It also encodes the consequence, which is the part that changes the mood of the story. Farther means earlier, and earlier means different, because the universe evolves, and because stars, galaxies, and gas clouds do not stay in place. So the light year is not just a conversion factor, and it is not a romantic flourish. It is a reminder that the universe is observed as layered history, with each layer constrained by the same causal geometry. This layered history is not optional, and it is not a choice of astronomers who prefer poetic units. It is enforced by light cones, which define horizons and the boundaries of causal contact, even in perfectly empty space. Some regions are visible, but not reachable, because the expansion of space can outrun any attempt to catch up. Some are reachable in principle, but not yet, because the time required is longer than the age of the journey so far. These horizon statements are physical, not conventional, and they do not evaporate when you change coordinate labels. They depend on the metric and on c as the causal speed limit locally, which is the piece that remains invariant. Even if we changed our simultaneity convention, the set of events that can influence us would not change, because influence is defined by the cone, not by the coordinate grid. The light cone remains, and it remains the same boundary of possibility. That is why the documentary's mystery never threatens physics, even though it sounds unsettling at first hearing. The one-way speed ambiguity lives inside a fixed causal skeleton, and the skeleton is what experiments keep confirming. Now return to GPS, because it is the bridge between philosophy and practice, and it is a system you can hold in your hand. GPS works by defining a network time, then enforcing it, and the enforcement is an engineering triumph built on relativity. It uses an inertial frame for propagation and corrects for rotation with the Sanac effect, because Earth is not an inertial platform. It models relativity because clocks and gravity matter, and because nanoseconds accumulate into meters. The satellites carry atomic clocks, and their rates differ from clocks on the ground due to both special relativistic time dilation and gravitational time dilation. The system pre-corrects those rates, then applies additional corrections based on orbital data and signal paths. GPS does not measure one-way C in a convention-free way, and it never claims to. It operationalizes a convention so well that it feels like nature, because the convention is embedded in software, standards, and continuous calibration. Cosmology does the same at a different scale, and the parallel is more than metaphor. It chooses a cosmic time coordinate, then turns redshift and brightness into distances, and then checks the map by seeing whether independent probes agree. In both cases, the map is a disciplined agreement between data and definition, and the discipline is what makes it reliable. The agreement is tested by closure and consistency, meaning the system must predict itself when you loop through the inference chain. So what do we really know about light speed once we strip away the misleading phrasing? We know the round-trip constant with extreme precision because it is tied to interference, resonance, and the most stable clocks we can build. We know that locally no signal outruns light in vacuum, and that statement is tested every time particle accelerators, lasers, and timing circuits behave as expected. We know that Lorentz symmetry holds to astonishing accuracy across energies and environments. We know that causal order for time-like events is invariant, meaning that if one event can physically cause another, every observer agrees on their order. We know that light cones are the geometry of possibility, and they are the same structure used in both relativity and cosmology. What do we not know in the naive sense, which is the sense that imagines a universal clock ticking everywhere? We do not know a convention-free one-way speed across distance, because across needs now, and now is not absolute. That is not a failure of instruments, and it is not a missing experiment waiting to be invented. It is a feature of space-time, where simultaneity is not absolute, and where the act of defining distant time is part of the coordinate system. So the central question resolves into a clean statement that is both satisfying and slightly eerie. Invariance of C is deeply physical, while one-way speed is partly definitional, because it depends on how we choose to synchronize separated clocks. Yet the definitional part is not empty, and it is not a license to say anything you like. Choosing simultaneity is choosing a coordinate language that must respect the causal structure, and the language is constrained by what can and cannot influence what. The universe seems to cooperate with that language, and the cooperation is the practical miracle behind modern navigation and modern astronomy. Across laboratories, satellites, and galaxies, the same rule keeps working, and it keeps working under stress. That cooperation is the lingering mystery we end on, because it is easy to miss how remarkable it is. Even where conventions enter, the cosmos remains rigidly self-consistent, as if it is enforcing a deep grammar beneath our chosen words. It suggests that C is less a number we measure and more a rule the universe follows, a rule that shapes every causal chain. It is the rule that keeps cause and effect intact, and it is the rule that makes prediction possible. So when we measure space in light years, we are not dodging miles, and we are not being sentimental. We are speaking in the universe's native terms, where observation is reception, and where reception always arrives from the past. Distance is time carried by light, and time is what we can actually observe with clocks and spectra. Light is the messenger that makes observation possible, and its finite speed is the reason the universe appears as a history rather than a tableau. We began by saying no one has measured light's one-way speed, and the statement still lands with a jolt. We end by saying the universe may not need us to, because the physics lives in what returns, what closes, and what constrains. It only needs us to respect the rule that light cones impose, because that rule is the boundary of all possible influence. Within that rule, our definitions become maps, and the maps keep matching reality, again and again, across scales that dwarf imagination. Across this journey, we kept finding the same pattern. No matter how advanced our tools became, light speed is easiest to confirm when it leaves and returns. From Galileo's lanterns to laser cavities and atomic clocks, the clean measurement is always a closed loop. One clock, one place, and a round-trip constant that refuses to budge. That is why modern metrology could safely build the meter on top of C, while still admitting a stranger truth underneath. The moment we demand a one-way answer, from A to B with no return, we also demand two distant clocks that agree on now, and that agreement is never free. Synchronization requires signals. Signals require travel times, and travel times are exactly what we were trying to measure, so the logic folds back on itself. Einstein's solution, split the difference, make outbound and inbound equal, doesn't cheat physics. It chooses a bookkeeping that keeps the laws simple and the light cone intact. Reichenbach's epsilon reminds us that other bookkeepings are possible, and yet every loop experiment, every interferometer, every resonator keeps reporting the same invariant structure. Lorentz symmetry, time dilation, and the causal order of events survive the choice, because they live in what space-time refuses to negotiate. In special relativity, we paid for that stability with lost simultaneity, and in general relativity we learn the price rises again, because curvature and expansion deny any single global clock. On the cosmic stage, the telescope never grabs distance directly. It receives arrivals, directions, energies, and delays, etched onto our past light cone. Redshift becomes a clock, not because it tells us where in miles, but because it tells us when in the universe's changing scale factor. The distance ladder, from parallax to Cepheids to Type Ia supernovae, is really a ladder of cross-checks that translate light's behaviour into geometry, while admitting that distance has multiple honest definitions. GPS brought the mystery down to street level, showing that even our daily navigation runs on an enforced coordinate time, corrected for relativity, rotation, and atmosphere. It produces one-way travel times only inside a chosen synchronization convention, maintained by networks of round-trip links and consistency. Cosmology cannot maintain a universal time service across galaxies, but it does something more profound. It lets the sky itself define the map through shared light cones and model-tested consistency, so the unresolved thread becomes the resolution. The one-way speed of light is not missing because we lack cleverness, but because one-way presumes a distant simultaneity nature does not hand us. What experiments can touch, with essentially unlimited refinement, is the round-trip constant and the invariant causal structure that rides with it. What remains adjustable is the coordinate story we tell about distant now, and that freedom changes the narration, not the observable plot. Cosmic horizons complete the picture, because they are not a failure of synchronization, but a boundary written into space-time itself. Beyond them, no convention, no clock transport, and no technological upgrade can pull new information into our world line. Light speed, fixed in every local lab, becomes the universe's rule for what can ever be known, and what must remain forever outside our evidence. In the end, the light year is not a poetic alternative to miles, it is the measurement that matches what we actually observe. It turns space into time on purpose, because the universe reaches us only through travel time, and every image is a dated message. When we speak in light years, we are not merely describing how far away something is, we are admitting that distance is inseparable from history. So if no one has ever measured light speed in just one direction, what are we measuring when we map the cosmos in light years instead of miles? We are measuring the part that is physically locked down, round-trip C and the light cone boundaries, then choosing a consistent definition of now to translate arrivals into a usable cosmic map. Light speed is both a fact and a language, a constant in our instruments, and a convention in our coordinates, stitched together by causality. And maybe that is the deepest answer. The universe is not built to be surveyed from everywhere at once, only to be understood from within the cone of what can reach us. The next time you hear a distance in light years, pause and ask not only how far, but how long, and what that delay is quietly telling you about reality.